Good morning, everyone. Welcome to the inaugural ACM IMS Interdisciplinary Summit on the Foundations of Data Science. David Madigan and I are pleased you are able to attend what we hope will be not just the beginning of a new collaboration between computer science and statistics, but also the beginning of a premier event focused on the foundations of data science. Data science is the study of extracting value from data. The techniques we use for extracting that value rely on computational and statistical thinking. The explosion of interest in data science recently is due to the advances in algorithms, especially machine learning, enormous computational power, especially clusters of CPUs and GPUs, voluminous amounts of data generated and collected, feeding data-hungry algorithms, and the rapid pace of technology transition of ideas from lab to market. With efficient algorithms, big compute, and big data, using statistical models to do prediction, exploration, inference, and reasoning about uncertainty now becomes tractable and scalable. The value gained from this data extraction accrues to the domain expert. A scientist gets value by discovering new knowledge. Is that a new exoplanet I see? A mayor gets value by data-driven decisions that can affect the community's livelihood. Given sea level rise predictions, how should I regulate housing in coastal neighborhoods? A CEO gets value that can be measured by the company's bottom line. How much revenue did I get from users clicking on ads? Thus, to work as a data scientist is not only to have a command of the foundational methods, for example, computer science and statistics, but also to work in the context of a domain. Today, we see data scientists working with domain experts. Tomorrow, we will see domain experts imbued with the knowledge of data science methods. Through our event today, we will hear about how far we've come in state-of-the-art data science methods, specifically deep learning and reinforcement learning, and their applications in science, healthcare, and more. What properties, such as robustness and stability, we seek of these methods, and societal implications regarding fairness, privacy, and ethics in the use of these methods as they automate decision-making about people. We will close with a discussion, including with you in the audience, on the future of data science. We have what I think is a dynamite set of keynote speakers, panelists, and panel moderators. So now for the thanks. I'd like to thank ACM, in particular Vicki Hansen and Pat Ryan, and IMS, in particular Xiaoli Meng, for instigating and orchestrating this collaboration. Our steering committee, Magda Balazinska, Joey Gonzalez, Chris Holmes, Yanis Ioannidis, Ryan Tibshirani, and Daniela Witten. Google and Red Hat for their sponsorship. And finally, NSF, in particular MPS Math DD Juan Meza and PD Nandini Kannan, SAIS CCF DD Rance Cleveland, and SAIS IIS DD Henry Kautz for their support for travel grants for some of our participants. And finally, the National Academies, who, while not a sponsor, has expressed enthusiastic support for this event and its future incarnations. Before I close, I would like to announce that both ACM and IMS intend that this event be the start of a longer-term partnership to support this burgeoning field of data science. Also, while today's event focuses primarily on computer science and statistics, I want to acknowledge that the foundations of data science also draws on other fields. For example, signal processing from electrical engineering, and optimization from operations research, and analysis from applied math, and more. David and I expect that future events in the foundations of data science will reach out to these fields. So thank you, and please enjoy the day. One housekeeping announcement: the wireless password is ACM 2019. It's also the password you can use to access the live streaming of this event. To get to that, you have to go to the event website, and I assure you, you are all smart enough to do that on your own. So now, let me introduce David Madigan, who is going to introduce the first keynote speaker. David Madigan is a colleague of mine at Columbia University. He used to be the executive vice president of arts and sciences. He's a professor at Columbia. He's a professor of statistics. He's very well known for a project on observational health data called Odyssey that's coordinated by Columbia. And he's a good colleague and a good friend. Thank you very much.
Thank you. Thank you, Jeanette. And just very brief, I'll add my welcome. We're excited this day is here. We hope this is the first of a series of events. It's my great pleasure to introduce the first keynote speaker. We have 3 keynote speakers and then a set of panels today. I think it should be an exciting day. The first speaker is Professor Emmanuel Candes, a professor of mathematics and statistics and electrical engineering at Stanford. He has won countless awards. I just mentioned that he's a member of the National Academy and a couple of years ago became a MacArthur Fellow. Please join me in welcoming Professor Candes.
Yeah, you can close this. It works. All right, can you see my slides? Okay, not quite. Anyway, so thank you very much, David, for the kind introduction. It is a real privilege to take part in this event, whose principle is very close to my heart. I'm not saying this lightly. At Stanford, I'm currently co-leading with Yuri Leskovich, a computer scientist, an initiative in data science, which I hope will be major, and that will bring together computer scientists and statisticians as we do today, but also many other scientists and domain engineers. And so this is the reason I'm happy to be here, because I want to learn about your perspective on data science so that we do a better job at Stanford. So at the preamble, I'd like to observe that over the centuries, we've certainly learned to build extremely powerful mechanistic models able to make astoundingly precise predictions, and our everyday life depends on these models. And the validity of this model has been tested again and again, and I really regard this as a crowning achievement of the human spirit. And I really like this quote from Richard Feynman, who said that 10,000 years from now, let's say, what we will remember of the 19th century is not the Civil War, but it's the discoveries of the laws of electromagnetism. And I certainly subscribe to this point of view. Now, perhaps equally exciting, although less noted at the time, was the fact that we discovered non-mechanistic ways of making useful predictions. And Galton, for example, in the late 19th century, introduced the idea of regression to predict a quantitative outcome from measured features. And a few years later, the gentleman you see on the right, R.A. Fisher, introduced the idea of classification, that is to predict a class label from measured feature. And you see the famous drawing from his Harris species classification problem. Now, if we fast forward to today, of course, we've made tremendous progress in building up powerful, non-mechanistic predictive models. I would like to single out 2 contributions especially. The first around random forest gradient boosting, XGBoost, and I'd like to single out the work of Leo Breiman and of Jerry Friedman, my colleague at Stanford. And of course, today we celebrate deep learning models. You'll easily recognize these 3 gentlemen, and they will later tonight receive the Turing Award for their contributions. And so these models are very, very powerful. At the same time, if you go around campuses, especially if you go around life sciences, there's a bit of a tension. You know, these models are extremely complex. They're not easily interpretable, and people are a bit uncomfortable with this. But I think this level of discomfort will ease with time, and I think we'll already see it easing because, you know, the opportunities that these models offer are so enormous that people want to use them to improve their science and their business. Now, having said this, there are two things we can absolutely not surrender. It's the replicability of science and of scientific findings. And by that, I mean that the scientific conclusions I draw today need to hold up tomorrow. And if I don't do this, then I don't know what science is. And also the reliability. That is, we're using these models to make decisions, and we'll have a panel about this. In environments that are more and more critical, it's extremely important to understand the validity of the predictions, to understand their uncertainty, and to be able to communicate this uncertainty effectively. And that's what I'll try to talk about. So we're going to see these two things in turn, replicability and reliability, in the era of extremely modern and complex machine learning systems. Okay, so what statistics can offer? Well, one thing we could do is to take these black boxes, let's say the deep learning with I don't know how many hundreds of layers, and try to analyze it. I don't know if you can do it, I can't. And so what we're going to do instead in this lecture is we're going to take a completely different route. We're going to want to use these sophisticated algorithms. Now I'm going to call them black box. I'm not meaning, it's not pejorative, I'm just calling them black box because they're hard to analyze. And we're going to try to build around these algorithms new statistical methods that will leverage their power, but at the same time guarantee replicability and reliability of these systems. And we're going to build wrappers so that we can make valid inference, draw valid conclusions from data. Okay, so this is the agendas for the talk. And so we're going to start with replicability. I'm sure you know we have a problem. There is a gigantic replicability crisis, which feeds the media on almost a weekly basis. If you see a drawing on the bottom, you have the cover of The Economist. You also have an article that Andrew Gelman, who will speak later, wrote in the New York Times in November. And so just to give you a flavor of this replicability crisis, it's not only touching fields like psychology, but it's touching the life sciences. Amgen, which is a company, a biotech company located in Thousand Oaks, California, what they did is they took 53 studies that they consider to be absolutely landmark in basic cancer science, and they try to replicate the findings. Recruit new people, try to replicate the findings. The report of Bigley and Ellis in Nature 2012, which triggered an enormous amount of attention, is that they could only replicate 6 of these 53 studies. Healthcare Bayer, which is a German equivalent, took 67 studies, perhaps some of them are the same, could barely replicate more than a quarter. And so we have an enormous replicability problem currently that we need to address. Now, why is this happening? I think it's happening because if you try to follow me for a minute, I think we reverted the scientific paradigm. It used to be, if the day of the great R.A. Fisher, that you advance a theory, the theory makes predictions, and then you test the data, you test the validity of the predictions against carefully collected data. But now data comes before everything else. We have reverted the first 2 steps. We have enormous data sets that are available prior to the formulation of scientific hypotheses, and people look everywhere. And so there's nothing wrong with this, but we have to rewrite statistics if we want to account for this fact that now data sets come first and we ask questions later. And so what I'm going to talk about is new tools to address some of these problems, right? To address the new scientific paradigm that we're in. So an example of a data-driven scientific problem, if you go to a life science department, we have phenotypes, for example, whether I have the Crohn's disease or not. I have information about genetic information about individuals. I can measure your DNA variations along the genome at 300, 400, 500,000 locations. Later on, I'll show you analysis of a UK Biobank data sets where we have 600,000 variations that have been measured. And there's a question that, of course, everyone wants to assess is which genetic variations will affect your trait. For example, getting the influence the risk of getting a disease. And I think in lots of data science, a lot of questions are like this. You measure a lot of things because you can, and at the end of the day, what matters? Now here we're a bit outside of predictive modeling because I don't care about predicting your disease status, I can just observe it, or I don't care about predicting your glucose level, I can just measure it. What I want to find is I want to find the factors that drive this glucose level up so that I can do research on them and not waste time. And so, of course, I want to be able to kind of identify those variations that cause or that make you more susceptible to a disease without making too many false positives. Because if I make too many false positives, then I'm wasting everybody's time. And that's not what science is about. So to formalize the selection problem a bit, we can imagine that we have individuals, and that's actually data sets we're looking at. They come with their X, for example, genotype information. They come with their Y, their disease status. And we want to find, of all these 500 mutations that we have measured, which one actually influence your disease status. And so to formalize the problem a little bit, we're going to say that a mutation is of interest to me if it changes the probability of getting the disease, even if I know the value of the other mutations. Right? So a mutation is interesting if it provides information about your disease status beyond what I already know. Okay? And so we're going to say that a mutation is not interesting if I know the value of other mutations, it doesn't change the odds of getting the disease. For those of statisticians in the room, and I know we're not many today, it would be saying that if you thought that this was a gigantic logistic regression model, I'm just interested in whether the regression coefficient is 0 or not. Okay. For the computer scientists in the room, I can imagine that I have a gigantic graphical model. I have a node of interest, Y, which is your disease status. I've measured hundreds of thousands of variables, but probably not all of them influence the outcome of interest, and I want to find a Markov blanket, like which ones influence the response. Okay, and as I said, we're in the age of complex systems, and we want to use all the good stuff I mentioned to detect which variables significantly drive the phenotype of interest. Okay, and now what's the problem? The problem is here I have a model which relates the covariates with the response. I use one of these black boxes to actually measure the importance of these variables. Presumably, a high score indicates that you're likely to influence the response. And here in this example, I have 500 covariates. I measure, and we like to think in this example that the points with the high scores are probably driving the likelihood of the response. But what I did is I just took the same model and generated new data, and I got something like this. And I generated a new data. The model doesn't change. I just randomly generate data from the model and use a black box to recompute scores. And I get this. A fourth time I get this. A fifth time I get this. As you can see, you see tremendous variability. And I think I cannot say it better than Yoav Benyamini, one of my stats hero, that really that's a problem of modern science. You see, I was trained in statistics to separate signal from background noise. And now modern science is not this. Modern science is a problem of selecting, among many, the promising leads when I have extremely noisy estimates about each one of them. And so that's a problem we care about. So just as a way to look, what do we do at Stanford to address this replicability issue? Well, we're going to try to build this wrapper around this black box. And so are people familiar with what is a SNP? Okay, very good. So if you don't know, SNP is just a genetic variation somewhere on your genome. For each measured SNP that I measured by the company 23andMe, for example, I'm going to create a fake SNP. So my laptop, the one you see here, is going to take a set of features that have been measured about Emmanuel and is going to select fake features. And the idea of the method I'll present is to run the scoring procedure using your deep learning, for example, on not only the original feature, but the original feature augmented with these fake features. And on this example, we see that, for example, the number of features that passed a certain score, let's say 1, or point like whatever is indicated by the black line, well, there were 49 original features or 49 SNPs that passed this level. But I can also see, when I run the procedure on the original feature and the fake ones, that a lot of fake variables, things I've created on my computers, I cannot possibly influence my SNP level because they were generated by tossing coins on my laptop. 24 passed this threshold. And what I'll try to convince you is that it immediately tells you that there are probably 24 among these 49 that have no relevance whatsoever. And so if you were to report these things that were above the black line, then probably 24 will be false discoveries, what we call false discovery, and you'd have a very high irreproducibility rate of 50%. Scientists following up on your study would waste 50% of their time. So now how are we going to make these features? Well, I know we're not many statisticians, but if you're a statistician, you'd say, well, I'm going to use permutations. That's going back to Fisher. I could think about, maybe I'm going to go close to my screen. The green guy is Emmanuel. I have his phenotype. I have his genotype in X. And I could actually try to think about matching, creating fake features by bringing the genotype of a random individual, the yellow guy. For example, Ryan. And use this as a control to calibrate the importance that the scores that the black box computes for the green features. All right, so that seems like a reasonable option. This is called the permutation method. Lots of people use this, not in this context, but in different contexts. And the thing, it really doesn't work. That is, what you see here are the scores that the black box gives to features. This is an engineered example, so I know what drives the response. And the sea-salt points are the scores the black box gives to features that have no influence on the response. And the dark blue points are the features it gives to the permuted features. And you can see that there is no way I can use this as a way to assess what's happening on the left. And so here it's very important to reason statistically correctly. This doesn't work. But if we use the knockoffs, which we're going to talk a little bit in a while, then I get new scores because I impute carefully engineered fake features. And now the scores I get to see seem to look like the scores that I've got on the left. And maybe I can use this as sort of a control group to use for calibration. OK. And that's precisely what we're going to do. So we're going to create features. And these features have a property. And the property is that if you give me a list of variables X, so I'm just going to show you, I'm going to give you the key ingredients. So you see, you give me a long list of features, X, which at the bottom is indicated in blue. So for some reason, my pointer doesn't work. So it's indicated in blue. My goal is to create a set of fake features in red in such a way, and now we can almost play a Kaggle competition, in such a way that if I were to take a true SNP and a fake SNP, and I were to swap them, and I were to give this data set to you, and I said, did I swap or not, you would not be able to tell. Okay, so this is a statistical construction that we need to apply. You give me a list of variables. I create a new list of variables in such a way that if I take a feature and a fake and I swap them, you cannot tell. That's a recipe. OK, so you can tell. And now, well, we're going to feed this thing into the black box. And now what happens is that when the black box computes the scores, if the feature has no influence on the response condition on the others, then the scores also you cannot tell. All right, and so it's indicated on this plot. On this plot on the left, you see the scores that the black box gives to features that are conditional independent of the response. On the right, you see the knockoff scores. Some scores need to be high, but you see that their fake scores are equally as high. And so OK, you can use this as a calibration. And now how are we going to calibrate? Well, now the black box scores stuff I know is fake and stuff I don't know whether it's true or relevant or irrelevant. And I start to put a threshold. And note that how I compute these scores is totally irrelevant. You can use a deep learning, whatever you want, to do this. And I'm just going to try to adapt the threshold until I get in a place where I know that the fraction of false discoveries is under control. By carefully observing what's happening on the right side versus what's happening on the left side. OK, and if you do this, it's a simple procedure. And if you do this, well, what the theory says is that, yes, I can take any black box, compute any feature statistics I like, and then I can tune this threshold such that what I want to call the false discovery rate, the rate of reproducibility, is controlled at the 10% level or anything like that. And that's a theorem, that's a mathematical fact, that if you apply this procedure, no matter how y depends on x, no matter what, the false discovery rate will be controlled. OK, for any black box. So you see this idea of this wrapper. OK, so we've engaged in, we have created a little knockoff factory at Stanford. And it's a cool topic. And if you'd like to know more about this, Stephen Bates, who made a major contribution, is in the room. You give me a bunch of features. I need to create fake features such that when I take any of them, I exchange them, I cannot tell which is which. And I think it's fair to say, thanks to the work of Stephen Bates and my former students, Lucas Jensen and Wenshou Wang, his student, for any distribution, we know how to do this. I consider this a solved problem. And if you want to play with this, we have website and code that you can go visit to learn how to make knockoffs. Now, we do all of this because we want to do science. And so we spend an enormous fraction of our time actually analyzing genetic data. I can only give you a snapshot. And the snapshot is this. Like, we have this UK Biobank data. Now, we're running these algorithms on 600,000 features, 600,000 mutations, on 350,000 subjects of British descent, as collected in the UK Biobank. And what the method does, it discovers a lot of interesting stuff. And we've tested the method. Does it discover things that are reproducible? So we applied the method on smaller studies. We did some meta-analysis. Yes. When it finds discoveries, they tend to be replicated in bigger studies and so on. We did a lot of meta-analysis, which means that the findings we find, we're extremely confident that they're actually real. Of course, 10%, that's the rule of the game, might be false. OK, and we can actually pinpoint locations on the genome where we think that very interesting things happen. And so we have created data science tools where you can scan the genome. And for a lot of phenotypes, you would be able to pinpoint locations of genetic variation on the genome where we think that something extremely interesting is happening. And again, you don't have to take my word for it. We have a website, codes, where you can use these ideas on your own data sets. All right, I want to make a plug for deep learning, one more. And that's, to generate knockoffs, I need to know the distribution of X so that I can build this exchangeability. And in some problems, in many problems, actually, I will not know what it is correctly. And so what we are thinking of is to repurpose these wonderful tools that you guys have created to actually generate knockoffs. And this is a bit crazy, but it works extremely well. So we're going to train a neural net to generate knockoffs. So if you think, in this room, people are literate. You've heard about GANs. And GANs is you train a neural net to make fake images. Here we're going to train a neural net to make fake SNPs. And of course, it's different because I've seen images. I've never seen a knockoff. So there's a big difference here. But bear with me for a second. So I'm going to train a neural net. This is going to generate knockoffs. And then we're going to play this two game where there's going to be a metric that's going to measure how well can you tell which is which. And so you're going to have a score. You're going to have a loss function. If I swap a feature, is it easy for you to tell which is a true variable and which is the fake variables? And then we're going to train these neural nets to improve knockoff generation until it's becoming very hard to tell which is which. And that works very well. And so we're very happy to use deep learning models to create fake features. And of course, we got this inspiration from great work in CS about the use of general adversarial networks to create fake images. Here, we just create fake SNPs that are undistinguishable from true SNPs so that we can go through our program. OK, so this, and if you want to build deep knockoffs, then there's also software for this. OK. All right. I'm going to move to the last part of the talk, which has to do with, can we make reliable prediction? How do I communicate uncertainty? So I've been in the business for a little bit. I work on the Netflix challenge. This was machine learning 15 years ago. Predict whether I'm going to like a movie or not. Honestly, if you get it wrong, it doesn't matter. And now it matters. Because now, as we'll hear later on today, we use machine learning to decide who gets into college, who gets paroled, who gets bailed. And so if I have a machine learning system assisting Stanford's admissions office, there are many ways you can get into Stanford, as you know. Now I'm going to be in trouble with my provost. She told me, anyway. And then the machine learning algorithm says that I predict your GPA would be 3.62 after 2 years of college. Well, what do I do with this? 362 plus or minus what? I really need reliable systems. But at the same time, I want to use this black box that I can not easily analyze. I need to be able to communicate uncertainty, right? And so one way to think about this is as follows. I've got a bunch of data sets, a bunch of training samples, x1, y1. Y is a variable I'm trying to predict. I have a new test point. That's a new college applicant. I see her features, what school she did go to, her high school GPA, SAT scores, extracurricular activities, whatever you want to throw in your model. And I have to predict a GPA. But now I'm going to ask you to do more. I'm going to ask you to predict a range. And so what I'm asking the machine learning system now to do is to predict an interval such that the GPA falls in your range 90% of the time. I say 90, it could be 95, whatever number you want. It's not irrelevant. So I want to build a system that does the following, that based on the candidate's high school identifier, high school GPA, SAT score, so many features, the GPA is predicted to fall in the range 3.4, 3.9, and if you were to deploy this in the world, it would be 90% accurate, 90% correct. And that's a guarantee you have to give me. OK. And of course, I want to use these models, because maybe with these models, I can get short range that are informative, because they can predict well. But can you actually compute the standard deviations of a neural net estimate? It's going to be quite tricky, right? So we're going to use ideas from a computer scientist named Vladimir Vovek, who introduced the field of conformal inference. But in this lecture, I'll give you some new developments. But I want to acknowledge that there's a field called conformal inference we heavily rely upon. So suppose that, well, I was in a perfect world where I could observe both, I knew the distribution of y and x. Everything is revealed to me. So I know the joint distribution of y and x. And so a person comes with his x, like say x equals 3. I know the joint distribution, so I know the conditional distribution of y given x, and I can therefore calculate the quantiles. And I can do this for every x, and therefore I can find, no matter what, I can find the quantile, the interval I'm looking for. And in some sense, it's best. But that assumes that I know the distribution, which is selling away the machine learning problem. That's assuming that machine learning is solved. Instead, I just have this. So what do we do? Well, we're going to try to estimate quantiles from data, and we're going to use a tool called quantile regression. For those of you who do a bit of machine learning, I'm going to basically fit quantiles by minimizing the pinball loss. And I'm going to get quantiles out of this on some training sample. Would this work? No. Imagine training a neural net. You get 0 residuals. That's not going to be very good. And in fact, if I give you a fresh sample, the quantiles you would get using this method would dramatically undercover. You'd say, oh, this range for this group of students is this, and in fact, it's completely false. OK, so we're going to adapt this a tiny bit, and we're going to build a wrapper around my quantile regression estimates, for which I can use XGBoost, deep learning, whatever. Again, the idea of building a wrapper. And now you give me some samples. I'm going to divide them into a training set and a calibration set. On the training set, we're going to run quantile regression, what we used to do. But now I'm going to see how well I'm doing on the calibration set. And now watch, because this is extremely simple. I was not sure I should present this because it's so simple. And what I'm saying is, OK, I have the green point. The green point are the calibration points. And I can fall within or outside of range. If you're within range, you're going to get a negative score. If you're outside of range, you're going to get a positive score. Now, what are these scores? I'm going to look at the sign distance to the boundary. How far are you from the range, from the endpoint of the range? Again, positive if you are outside, negative if you're inside. So I get a bunch of numbers. Let's say that I have a calibration set of 200. I have 200 numbers. I take the 90th percentile of these 200 numbers. That is the 180th largest value. And now watch. What I do is I adjust my confidence band to whatever was calculated before, and then plus or minus this quantile. That's it. That's extremely simple. Extremely simple. In particular, if I were to do a good job to start with, then if you follow what I'm saying, the quantile would be exactly at 0, so I would not touch it. If I'm conservative, then the quantiles would be negative. I would actually shrink it. If I'm anti-conservative, I would extend it. OK. And now how does this work? I give you a fresh sample. You want 90%? It's 90.09. That's OK. So I know I have to stop. So this is a result. This is a fact. It's a fact, again, another mathematical truth that this very simple method can give you the precision you want. OK, and that works no matter how the data is distributed, any sample size, any black box algorithm you might want to use to fit the quantiles. OK, we've applied this to medical services when we need to predict medical expenditures from lots of social economic status variables, trying to use how many visits to the doctors you're going to make, hospitals, and so on. And this method is unbelievably precise and accurate. You want 90%, you exactly get 90%. You want 95%, you exactly get 95%. OK. So, and again, we have code and stuff you can use. So my time is up. But I thought that as we are living, and we'll hear a lot about it today, we're living in a world where machine learning is applied to other things than Netflix, and things that are of critical, that support human decisions that are extremely important. It's important to make it trusted. So I've discussed two things: to build a wrapper around the algorithm we want to use so that we do not run into the problem of reproducibility. And of course, this is dramatically connected to causality. Of course, if I knew how to solve the causal inference problem, the reproducibility problem would go away. But there's an arrow in the other way. In fact, I can show that sometimes controlling for the false discovery rate will actually control for the false non-causal rate. And I think it's extremely important to be able to assess uncertainty when we make predictions, especially when a student comes up and has been admitted to college. I've shown you a method that would give you valid coverage no matter which group you belong to, no matter what protected characteristics you have. And I think it has to inform fairness, obviously. And with this, I'd like to thank you for your attention.
So in the interest of time, could the panelists, please, for the people for the first panel, please go to the stage. And while we're doing that, if we could take one question from Professor Candace over here. Yes. Yep.
I have a question about the black box. So now you have reproducibility and reliability. So how would you have a favorite black box? I have one favorite black box. Now you have two measures. So in a lot of examples we tried.
So I'm sitting right there, so I'll wave at you and stuff. Okay.
So the question is that now that we have a way of making the black box reliable, do I have a favorite black box? Not really. But in a lot of examples we've tried on UCI data and in genetics and so on, I found that, for example, UCI data XGBoost is a good black box to use if I want to predict medical expenses, for example, from various features. For genetics, it seems like genetics is fairly linear, like somehow features contribute in a linear way. I found that regularized logistic regression, the LASSO, pioneered by Rob Tibshirani, sitting on the second row, are very useful. And we use a lot of different black boxes.
Okay.
But yeah.
Okay, thank you very much.
All right, so I guess black boxes are a great segue into the next session. So this session is an open panel. We're going to be talking about deep learning, reinforcement learning, and the role of methods in data science. It's a pretty broad topic. Rather than me introducing all the panelists and listing their accolades, I've asked each to give a short introduction, your name, and what you work on.
Hi, everyone. I'm Shirley Ho. I'm a group leader of cosmology cross data science at the new institute called Flat Institute, which is 100% funded by Salmons Foundation, and I also have a joint appointment in Princeton University.
Hi, I'm Shyam Kakade. I'm a professor at the University of Washington in computer science and statistics. I work on machine learning and artificial intelligence with a particular focus on the mathematical foundations and a focus on reinforcement learning.
Hi. Hi, I'm Suchi Saria. I'm a professor at Johns Hopkins. I direct the machine learning and healthcare lab there. And my work is focused on two fronts. One, as more and more data becoming available in healthcare, how are healthcare delivery models going to change? That means how is the practice of healthcare going to change? And what that means is what are some new tools, new pipelines we will need in order to be able to change the way they practice to bring data at the front lines. And then the second aspect of it, very related to it, is what are fundamental methodologies we need in order to be able to make machine learning and data science available at the front lines in a safety critical domain like healthcare or education. And along those lines, we do a lot of work on taking messy biased data sets and working at the intersection of causal inference and machine learning to produce exactly the kinds of things Manuel was talking about, which is safe and reliable ML.
Hi, I'm Manuela Veloso. I am currently the head of AI research, a new effort at JP Morgan Chase. And I'm also on leave from Carnegie Mellon University, where I've been a professor for the last 32 years. So I am in this transition from academia to understanding the corporate world. And basically, it has been a discovery of the complexity of the real world, in particular the financial domain. I'll tell you more about it.
Excellent. I should introduce myself. So my name is Joseph Gonzalez. I'm an assistant professor at UC Berkeley. I study research at the intersection of machine learning and systems. So the format of today's panel is I'm going to ask a sequence of questions. There are open microphones in the room, so if you want to add or elaborate on a discussion, please feel free to join in. I will start with a few fairly high-level questions. Since this is the first panel of the day, I thought it'd be fun to define data science. So tell me a little about what data science means to you, how it affects education and research in your area, in your discipline. Yep.
Let me just start first by thanking Joseph to actually organize this panel. I would like to paraphrase what I learned from actually being you on an IMS presidential address a few years ago on what data science is. And it says, it is the study of generalizable extraction of knowledge from data. And for me, this includes methodology and also the tools that you actually need to extract the knowledge, the domain knowledge that not only helps you discover the knowledge that's furthering your understanding of the whole world around you, but also maybe producing the data that's required. And finally, also the infrastructure, software, and hardware necessary to make this possible. What's more is that I think we need to communicate the knowledge out to the community, to the relevant community. And I think that's a really, for me, succinct definition of data science.
So data science. So I think, maybe I'll start with a joke. So I think I've heard a data scientist referred to as someone who knows statistics better than a computer scientist and computer science better than a statistician, which, I think to a large extent the field came about because while we had these different disciplines, there's a group of people that need skills in a variety of different areas, and there's a functional definition, which is it seems like there's a group of people who should have knowledge so they can work with domain-specific experts in a variety of different areas, ranging from, say, bio, health, to various technology areas. And I think on the educational side, there's just been tremendous demand, and clearly machine learning is one of the core areas. So, and it feels like everyone needs to have foundations in ML to do it.
I agree with Shyam and Shirley. I'll just add one comment here. Some of my observations from the last few years has been, if you look at fundamentally the excitement in the last 10 years in this field, it's partly been from achievements like, autonomous driving or web search. In effect, like massive engineering tools that deeply utilize data in order to provide value. And the thing that's interesting about that is, I think if you look at a lot of academic data science work or industry data science work, a lot of it is around taking large amounts of data and doing discovery exploration. But I think a component that is very fundamental, which the field desperately needs, is thinking about principles of engineering and reliability engineering. So if you look at other fields like nuclear engineering or civil engineering, where you're looking at safety critical disciplines, there's sort of a very clear notion of like, if you're going to deploy something or if you put something out there, is it working? Does it work the way you expect it to work? And I think as data scientists, we've been given a lot of responsibility and freedom to go in very important areas and start influencing and informing decision making. But that engineering principle of being able to guarantee that we understand what we've built and we can stand behind it, and we're not going to, make catastrophic decisions is very key, and I think at the moment sort of missing. So that wasn't, so just sort of to add, I think this is sort of, if you had to broaden out sort of data science, I see this as like a fundamental component of computer science, computer engineering, and engineering writ large that needs to be brought into data science, and something I'm hoping will become part of the definition.
So I don't know what is data science, but I do know one thing, that it's very, very takes my sleep at night, which is the following. Throughout my life, I've been working on AI, and AI is this kind of like a fascinating research goal to try to really make machines that are able to get as input some kind of like data, make decisions, and actually actuate. So there is this kind of like loop of perception, cognition, and action, or data, decision making, and actuation. So there is this thing. So I see data science as providing the substrate to actually being able to close this loop between the data, the decision making, and the actuation. Let me just share with you something about this data science problem, which is something that sometimes we, in our engineering of thinking about the problem, we may forget. The challenge for me from data science, when combined with decision making and actuation, is that this data is generated from the most diverse sources of the world, from different frequencies, different ranges, different certainty, different everything. So data is not a unique concept. It's this tremendously, how can I say, messy kind of concept. So it's worse than languages. So languages, we can even like, it's a finite number. Even if it's very large, it's a finite number. Data is completely unbounded in its definition from a scientific point of view or from an engineering point of view. So I really think that that is like the challenge here, is that we have to still use such information to equip a computer with ways to support humans with decisions, to support humans with prediction, to eventually even take into their own hands making decisions based on data. So that's why I think that this data science field is complex, or this data processing, data use is complex, is because of this horrible and at the same time amazing opportunity of these unbounded messiness of data, which has a lot of information, a lot of knowledge, but it's kind of how do you bound this problem in general? So that's what I believe data science is all about.
Actually, so touching on this discussion of action, something we come across in systems is thinking about data science as a science or an engineering discipline. And as we start to use data science and learning techniques to manipulate the physical world to make decisions for patients, to alter how we take or how we approach scientific problems, maybe what are the big concerns we should start to think about?
Well, I don't know, but in some sense, so I think just to finish these thoughts, I think that ideally what we would like to have, be it in any data set, be it health-based, finance-based, transactions, any data, we would love to have some kind of description of the data, clean and all kind of like uniform that we could feed into a neural net or any machine learning algorithm, and then it would work. I am amazed by how hard it is. I wrote this simple white paper called The Curse of Exceptions. It's not dimensionality, it's exceptions. There is not a single case I talk with at the firm that doesn't say, oh, this is how transactions are supposed to be recorded, but those transactions of this nature, which is maybe 1% of the whole thing, are different. And then we say, okay, but something else is whatever. And I cannot stand any more buts, you know? And so in some sense, I keep saying, why can't we, how are we going to get all these buts part of like not being pruned out by outliers, not being considered like noise? They are buts from the point of view of humans. They are not just noise. So this is a little bit of a difficult problem for me from an engineering point of view. How do you represent them? And from a science point of view, you know what? Sometimes these but things, these like whatever, are the ones that have more information and are the ones that you really don't want to miss. Yep. So there's the science of these outliers, which we all know. Right. And there is also this problem of the engineering, of not missing it. Anyway.
Comment? So we definitely teach this in the data science class, how to deal with dirty data. And it's funny because it ends up dominating a lot of the discussion in the class. And so your comments about what data do you drop, is dirty data something you get rid of, or is it actually the signal that you're looking for? A lot of you work with real data. Can you talk maybe about some of the kinds of dirty data you've seen and data where the dirt was actually the value?
I can't take this. I'm by training an astrophysicist, even though I have a computer science degree from Berkeley, actually. But we deal with a lot of very, very diverse data sets, going from optical data, looking up in the sky, infrared data, also radio data, and they're very, very dirty, just like what you were saying. But I think getting them clean is one big problem, but I actually have seen the big problem about data science these days are how to interpret what we've learned from the model that actually echoes Emmanuel's talk earlier today, how to understand the black box. Scientists are very early adopters of data science. We've been extracting knowledge from data for eons. Let me start with a story where Sir Eddington actually looked up into the sky when the solar eclipse happened in 1919, after Einstein proposed this new theory of relativity. So he went up and collected these photons from Taurus constellation and say, okay, had they moved because the gravity field of sun has distorted these photon trajectories? Has it moved according to Einstein? So it did that not just in one location, but in 3 locations on Earth, and they extract this data and did the statistical analysis for this, right? But now with these new methods like deep learning or reinforcement learning, a lot of these neural nets, we don't have a fundamental understanding why it works. So that makes a lot of scientists very hesitant to adopt deep learning in particular as a new data science methods, and if make predictions, for college applications, for example, how do we deal with that? If you're going to teach university students, this is what you're supposed to do to discover new knowledge and new frontiers, how do you trust it? So I think that's the next big step to think about.
A different perspective, if we come at it from the machine learning angle, is dirty data might just be another source of just a data from a very different distribution, and how do we actually learn from such data? So if I think of an analog from computer vision, which was provided really one of the most compelling breakthroughs in deep learning, where there was a dramatic improvement in quality of visual object recognition. And kind of across the board, the representations these methods would find would start transferring to many, many different tasks. But one of the challenges in this area, when we start moving to things like autonomous vehicles and robots which interact with the system, they're often on noisy cameras, or even if we pay a lot and get very high quality cameras, the pictures are from very different viewpoints and angles, and they're from a very different distribution than what we trained on. And one way of progress is we could say it's just dirty data and find other ways to label it. A different way is we start thinking about algorithms where we can generally start transferring learning. So with a small amount of, say, poorly labeled data or corrupted data, maybe not adversarial corrupted data, but corrupted in that our camera's noisy or some robotic arm breaks down, how do we actually have methods which learn to adapt very quickly, and as they learn to adapt quickly, they can start adapt more quickly on other problems. And I think this is a pretty promising direction to address some of these questions.
So, yeah, I agree with Shyam definitely on this topic. So over the last few years, so one of the reasons I moved to Hopkins was I was kind of feeling that, it's been super fun to work on hard machine learning stats papers, but there was sort of a little bit of this hypocrisy internally, realizing that, I was like, practically none of them had been translated at scale. Practically it was very unclear to me that they were really going to influence human decision making. So I ended up moving to Hopkins, working very, very closely with the health system there. So health system means the hospital leaders, the C-suite leaders, and over the last 3.5 years, my naivety led me to agree to thinking that we should take some of the ideas we're producing in the lab where we think there's really an opportunity to influence the clinical decision making and partner with the health system to deploy these. And so we've now deployed some things that are available, being used by 4,500 clinicians, have scanned over 1 million patient records, are deployed in over 90 clinics. And when I did all this, I didn't realize how hard it was going to be, and sort of some takeaways from that. So one, like when we write papers, we very often start with very simple, clean, kind of single objective functions. But what we found is when you're deploying something in practice, in order to triangulate whether it's really working, you need mixed methods. You need the ability to triangulate accuracy, reliability from a variety of different ways, because often the notion of a gold standard, especially in medicine, is very unclear. So it's a combination of all the way from measuring generalization carefully, because there's lots of different ways in which you'll see shifts in the environment, shifts in the patient population, shifts in the ordering patterns of physicians. So you really want to be able to learn, you want new algorithms, and it's led to a slew of really exciting work, all on trying to be able to provide algorithms that provide stable estimators, or provide estimators that generalize and are robust to these kinds of shifts. But in addition to that, methods that can measure in real time test time reliability and auditing. So when something is becoming available to a user, can you somehow assess whether this one is at risk of being a place where you really aren't all that confident? So basically, really deeply engaging in practical work has given me sort of a level of a bit of a humility with, sort of needing kind of multiple tools in the toolbox, all the way from both quantitative but also qualitative points of view, to be able to assess, to approach the problem to see, well, how do we get rid of the many noisy forms of, or how do we tackle the bias that's in the data? How do we measure whether it's working or not? How do we put systems in place to monitor? And how do we try to think about maintenance from the point of view of, has the system drifted so far that it needs retraining, retuning? All things that I think are very exciting.
Yeah, so following up on on sushi, that actually I believe this is very important. So it's also interesting to try to understand what is the role of humans, after all, if data is so powerful. And I actually have faced this debate all the time. For example, at JP Morgan, we have people that are real experts of operations, of all sorts of businesses, and then they also produce 80 billion records of data of transactions all over the world. So there is this thing that it seems that in principle, the 80 billion records or the 100 billion records or the trillions of records that capture how many transactions the firm produces would have all the knowledge, would have all the models of how things work. I mean, because it's so large, it has spent so many years, it has spent all the regions of the world, that you wonder if you have a machine learning algorithm, an AI algorithm that analyzes all that data, are we closing all the knowledge involved in these processes? And it's interesting to realize that somehow even these enormous amounts of data does not capture everything that eventually the humans know. And so I am fascinated also by understanding this trade-off between how can the humans contribute to fill in what inevitably maybe the data doesn't capture. So there is this thing about us creating more and more data. We have Fitbits, we have GPS, we have all our health, we have all our finances. And on top of that, there are still humans. And that's really beautiful that we don't have reached the point where by capturing all this data, we are capturing everything that humans can actually understand. And for that, for example, I tell you, there is something that I find fascinating. So if you have not watched that movie of which is a true case of the landing on the Hudson, Sully, this movie Sully, you actually, I assign as homework number 1 to watch this movie. And why is this so compelling? So this man takes off from LaGuardia, there is a problem, and in about 300 seconds, it's not more than a few minutes, makes the decision against even guidance from LaGuardia to go back and another place to go in New Jersey, in Jersey City, whatever it is. This man decides to land the plane on the Hudson. And, you know, for the magic of this human and everybody else survives this thing. Fantastic. So he's asked, how did you make this decision, given that you have never landed on the Hudson? There was no data ever to be learning from. And there is this thing, and I tell you, go to this movie. I assign you as a homework, I'm telling you. And there is this term that Tom Hanks says on the movie. I eyeballed the situation. And I have this word in my mind thinking, what type of data will enable an AI system to one day eyeball a situation, was not measuring anything, was somehow had done this when he was a pilot in the old days, a fighter. I mean, what in the world is this eyeballing thing? So when people ask us, I mean, is data, machine learning, AI going to take over the world and humans and everything? No. Just go to this movie and see how it says I eyeball the situation. And none of us writes papers on how does AI eyeball a situation based on data. So that's what's beautiful about humans, data, machines. And yes, we can capture a lot of patterns, repetition, we can help a lot. But there is this magic that our DNA enables us to eyeball situations and to make decisions that are not definitely supported by data. So that can put us all we have jobs for the rest of our lives, I guess.
Yeah, if you want to say something.
Can I quickly respond with this, because I think it's an excellent example of discovering knowledge or having intuition about the system somehow. This eyeballing, this intuition that humans developed. And I think as a scientist, we have this scientific intuition, like Einstein didn't have data, right? He just eyeballed. I mean, he's very smart, but he just eyeballed a situation and figure out general relativity, and your GPS will be wrong by quite a number of feet if you don't have it correctly. So how do we use that to further this thing that I think Suchi also talked about generalization, or Sham just talked about transferability? I think there's certain intuition here that might be in play to come back to make transferability and generalization possible and more broadly applied in machine learning also.
Go. So I don't, I think the intuition is important. I think there's a case to be made that there are disciplines where things like this might occur in the broader realm of machine learning controls. So, one viewpoint of ML is we're just doing this predictive learning, and this is clearly an out-of-distribution event, and you can't do anything in this usual IID setup. But if we think of something like controls, there's an area called like model predictive control. And I would argue that one of the very successful ways of dealing with robotic systems is you have a model which does look-ahead planning based on the current situation you're in. And this works very well, like in these toy robotics, even real robotics examples. You kick some robot over and it's in some different configuration. The thing that's trained on a setting where there's no kicks can't do anything, but the thing that does look-ahead planning in this new situation, even with relatively crude models, can adapt. So this sense of how do we mix planning with crude models in these systems, actually, there is a case to be made that these things are pretty robust to out-of-distribution events, and the entire area of MPC planning in controls tends to be about stability and model mismatch situations. So that's one.
So building on this discussion of methods, so one of the topics of this session is methods. So we have to broach a topic. What are the methods we should be paying attention to? What are the methods that are overhyped? How have methods transform what you do? Who wants me to start?
You want to start? I'll start. So since I'm fresh from ICML from yesterday, where I gave an equally passionate 3 different talks on the topic, but again, I think going back to the thing I had said earlier, I really would love, I think in the work we do as scientists, we, data science, scientists, I think to us engineering is a dirty word. I grew up very much thinking it's completely hilarious to me that we think, oh, but that's engineering. They love, oh, that's just engineering. You don't want to do that. And I just think it's hilarious. And by the way, I'm appointed in an engineering school, also in the school, also in stats, which is in a different school. But I think going back to this idea, there is just no way we're going to succeed in building, informing, and influencing important pieces of how we progress, we make decisions, we move forward as a civilization if we can't bring back engineering principles into it. And engineering principles of does it do what we expect it to do? Do we understand what it should be doing? Do we understand where it breaks down? Can we quantify and forecast reliability? And I see so little to no discussion of this. And I really hope that as we start thinking, deploying, this becomes sort of a much more talked about topic. And part of the issue I see is that the only reason people are even talking about it is because we have more complex prediction methods now, and there's desire to, a lot of the focus, if you look at a lot of the papers, a lot of the young graduate students, I think the way you tell the temperature of a field is you ask a second-year graduate student, what do they want to work on? And they'll all say, oh, I want to work on deep RL. And so the question is, well, what about it? And they're very excited about playing with new architectures, how there are more layers you can add and more knobs you can tweak. And that to me feels like, design without any engineering principles.
Let me follow up here. Because I'm an electrical engineer. That's just what they say. And then a computer science is an AI person, but in the old days, I used to be an electrical engineer. And so one thing, and I'm still an engineer, One thing I think that it's important for us to come back to the data and the methods. There is these very powerful methods that we have now, these reinforcement learning methods, or methods that enable us to combine data with decisions and feedback, which reward, which are very powerful in trying to close this loop of analyzing data and using the data, and eventually observing the use of the data, getting reward, and staying in this cycle. However, the power of these techniques, this method of reinforcement learning that we all use one way or another, is very kind of like dependent on the ability to explore, the ability to actually let the machine, not while learning, not just use what it already knows, but to try to navigate that gigantic space and try to jump around, trying to find the optimum somewhere. Now, when we are in the real world, imagine me like being at JP Morgan and trying to say, okay, let's try to experiment, give a loan, don't give credit card, do this in the real world to see what is actually, how to learn this policy, this optimal policy. So we have these techniques that analyze data and extract to predictions, classification, which are fine in terms of like how you use it. To use this data to actually do reinforcement learning, I don't think we can survive without simulations. We cannot do this search of this gigantic space in the real world. So what at JP Morgan, for example, we are building like this simulator of all these operations in the bank, eventually to try strategies to train the system on crisis, because the real world, even if it provides a lot of data, unfortunately, it's boring data most of the time. I mean, it's like what happens every day. It's like the same thing over and over. So it does not prepare an AI system for the unknown, which is really when you need to be able to have an AI system that says, oh, this is like this rare disease of cancer or something, alert the human for something. So what I'm saying is like this. And I talked with Suchi yesterday on the airplane about this. I mean, we need to invest on great simulations. So while we look at the data, if that data enables us to generate realistic simulations where we can try all sorts of now stretching the reality of the world in all the directions, we may be able to, in fact, have an AI system that can discover the cure for cancer, an AI system that can end poverty, an AI system that can do amazing things because it's able eventually to try all different dimensions everywhere. So I think that our methods are very powerful, but the connection between our methods and the actual impact of using the data, unfortunately, even if we have billions, trillions of data, requires us to also worry on simulations. So reality is generous in giving us data, but we are not going to be able to just build upon the data to make great decisions, one way or another.
Yeah, so like Suchi, I also just came back from ICML, so I'm definitely recovering from a lot of the hype. And so before I touch on that point, I'll also just reiterate what Manuela said. This point of utilizing simulators there are a variety of fields where people are starting to think about this more, and how do we incorporate some notion of look ahead in real-time systems. And this is clearly important. It's clearly utilized in other areas. And there's, I think, a kind of rich interplay between this like domain-specific questions and how do we use various knowledge we have about the world in real time. Now, maybe I'll briefly talk about this hype question. So, and with regards to methods. So, it's a little difficult in that some of the most impressive results we see are also coupled with a lot of hype. And maybe I'll give one example. So less than a year ago, there was, I think, a pretty remarkable breakthrough in natural language processing from the Allen Institute 2, AI2, utilizing this particular language model called Elmo, and it kind of worked very, very well in a number of different other tasks. And Google built an even more impressive one called BERT, and did even better. And the results really across the board on human-level interesting language tasks improved. And more recently, there was a pretty spectacular language model from OpenAI called GPT-2. And you look at the generations from these language models, and they're very impressive. Even many of my NLP colleagues were they were kind of shocked by how good the generation. So they literally trained the language model on a ridiculous amount of data for like weeks on very, very powerful compute resources. They generate, then they seed the language model with like one sentence and see what it has to say, following up on that one sentence or a couple of key words. And it really does keep track of various long-term dependencies. It's pretty coherent. And the results are spectacular. And yet, when it's released, it's coupled with a lot of hype in that it's released on a blog post, and it's a bit of a shameful post because this release was saying that, oh, we're not going to release the full model because we're concerned that it'll be used for bad purposes because the language model is too good, and it really reads in a pretty distasteful way from a scientific viewpoint. But on the other hand, the results themselves were extremely impressive. So there is this coupling between kind of hype and substance, and sometimes you get the two just completely together without even a release of a paper. And that would be sort of at least one example. And it's worthwhile having a look at this, but the results are pretty spectacular.
Yeah. I will touch on what's the most transformative methods as far as a scientist's point of view, because I'm coming from the science side. It also really strongly draw on what people have just discussed, especially on simulation and search and optimizing and generalizability, interpretability. So for scientists, what's most transformative method, if it exists, and hopefully it will exist, is the one that can be used to discover true new knowledge. And what do I mean by true new knowledge, right? So I was talking to Pushmeet, the DeepMind lead, recently, and we were discussing what the 3 sets of problems that are interesting and we should really work on. One is simulation, the other one is search and optimize, and the third one is actually knowledge discovery, which is really, really hard, something that's not in your training set. Going back to the anomalies, going back to that one thing that you need to simulate to get at. So how do we do that? And is there a method that would discover truly new knowledge that is interpretable, so that we can bring back and explain to others how we came to that, which also touch on, can we make it not so distasteful, but actually something applied and people can reproduce the data, reproduce the method. So I think if that method exists, I definitely get a lot of scientists out of jobs and get myself out of job.
All right, so we don't have a whole lot of time left. And Sham kind of touched on a topic that we've run into. There are too many papers. And ICML, my students are just trying to summarize abstracts, and it's still taking way too long. And on top of that, we have publications and blogs on arXiv, and it's becoming like the paper is something that happens long after the results have been disseminated. Maybe some thoughts on how we can address this as a field.
Do you want to take it? Start us off, Jan.
Well, I guess we better apply our own science to the problem, right? So we are all doing AI, data science, and now one of the targets is our own papers. I mean, the whole world is contributing advances. So
some of my students are making strange claims, like we should be posting on GitHub and focusing on getting users of our software before we focus on the results or publishing the results. And that's different than the way I would look at the world. Is that something we should be thinking about?
So maybe a broader point is that there's kind of the traditions of how we work in academic institutions and concepts like tenure, how we judge people, and then there's a separate question of what's the most effective way to disseminate knowledge. And I think often these two are coming in to contrast, and coupled with the fact that, look, people are people. We want to, there's an inherent nature to try to stake your claims on things and just personality. So it's important to have some ways to try to mitigate these effects. And there's some argument that I'm not. I'm reasonably open-minded to fast publication cycles to get ideas out, but we should just have a little more of an understanding of what our objectives in doing this are, because I think there's a reasonable model to try to communicate ideas quickly, and I think the field has benefited by a lot of communication, and certainly just the access of GitHub and Archive supports this way of communicating knowledge. That isn't necessarily the best way in which we can attribute certain ideas to certain people, but so there's, I think there's just a lot of social factors that compound these effects. But I'm reasonably open-minded to kind of the, I guess it would be higher p-values in that I think it's kind of okay to have more failures in papers as long as we reproduce things and get ideas out there.
My student has a crazy idea, which is to use the AI system to look at all the papers and extract the important things and summarize for us.
That's what I was saying.
So I don't have to do any work.
That's what I was
That's a
saying.
great plan. All right, we're out of time, so let's thank our panel once more. Say again. Oh, so we have a break until 10:35? Yep, so we have a break until 10:35 sharp.
Okay. Is my microphone on? I guess it's not on
No,
yet.
it's not on. No, they will turn on for you.
Please settle down. Please settle down. We're going to start now.
Hello. Let's have everybody get seated. We're going to start the next panel session. My name is Ryan Tibshirani. I'm a faculty at Carnegie Mellon University. I have a joint appointment in the Department of Statistics and the Machine Learning Department. I'm thrilled to be here. I'm really excited for this next panel. We have an all-star cast of esteemed panelists. And to follow suit from the last panel, I'm going to have them introduce themselves. You guys can maybe say, like a word or two of your research interests as well. So please go ahead and start.
Should I start?
Yes.
Is the mic on? My name is Xiao Liman, and I am a professor of statistics at Harvard, but I'm here actually on behalf of IMS. I'm the president of IMS. I want to particularly thank the Vicky Hansen and the ACN for really having this great partnership here. And I understand that we have a very small presence here as IMS members, but it's okay because you guys are like, yours, you have 100,000 members, we have 4,000 members, so proportionally we're not that far. So I just want to mention that. And I also want to mention that I am also the founding editor-in-chief of Harvard Data Science Review. And the reason I mention that is not just to plug for Harvard, because this will be relevant to what I'm going to say later. But I do want to mention that it's much harder to get into Harvard than to get into Stanford.
My turn? So my name is Bin Yu. I'm a professor of statistics and EECS, also computation biology at Berkeley. And actually, I was, to connect with IMS, I was past president of IMS, and Shirley kindly mentioned my presidential address called Let Us Own Data Science. I'm very glad to be here. And my research and my group, we have been really trying to do two different things. One is to really embed ourselves in scientific research, genomics, and neuroscience, for example, precision medicine, at the same time build unifying principles and framework that will be applicable to the whole data science pipeline or workflow. And so this panel, especially stability, is something I have been advocating for the last decade, so very glad to be here.
So good morning, everyone. My name is Richard Samworth. I am Professor of Statistical Science and Director of the Statistical Laboratory at the University of Cambridge. I am not the IMS past or present president.
That's good.
But I am the co-editor of the Annals of Statistics, which is one of the IMS journals. So I work on a variety of problems in non-parametric and high-dimensional statistics, including shape-constrained estimation, variable selection, classification, lots of other things.
Yeah. Hello, everyone. I'm Alexander Madre. I'm a faculty at MIT. And I work on quite a number of things, but I think the most relevant things for this setting would be that I try to make sense of why these modern machine learning methodologies like deep learning work. So I call it like science of deep learning. And the other thing that actually turns out to connect to the first one is I think about how to make our machine learning more robust and reliable. And I want to mention that I want to make a claim that it's even harder to get to MIT than into Harvard.
Thank you very much.
So I should say that Berkeley is the hardest to get in.
No comments.
Okay, so now that we're done discussing the pecking order of universities, so our topic today is robustness and stability, and this is the format that we're going to shoot for, although of course, could go off the rails, and that could be fun too. I'm going to float two questions, and our panelists are going to discuss them. And then I'd like to save like 10 minutes at the end for audience questions, so I really encourage people from the audience to come up and, especially in the last 10 minutes, ask some tough questions. So let's start off just by setting the stage. Let's have our panelists discuss what do stability and robustness mean formally? How can we think about them? Have they evolved in statistics and in computer science differently? Are there important differences that we should be aware of? And what can we learn from each other? So in any order. Anybody can begin.
Okay, thank you. So I like to define stability or robustness at a very meta level. So you have a process, you have input, and you have outcome. And you have a metric to measure the outcome deviation from something. So stability at the meta level is about you perturb the input in some way, and the outcome changes, and you observe this change. And also at a high level, you also have two issues. One is to measure the stability of a given procedure. The other is actually enforce stability or robustify things. So these two issues counterplay with each other. And at the philosophical level, I think common sense, stability and robustness, you can go by philosophy of like Plato says something like knowledge has to be tied down, but your opinions can change over time. And historically, I think statistics, uncertainty is a specific form of stability in the sense that the perturbations sample-to-sample variability under a probabilistic model, and variance L2 can be a measure of stability. And maximum likelihood, you can see, is a way, actually, it's a stable procedure. We don't see it that way, but if you look at all the parameter estimation methods, maximum likelihood under conditions has the smallest variance, so the most stable. And today, we really think about much broader sense of stability, and you have robust control theory, which is also kind of now under the purview of, I would say, data science at large, and also robust optimization. Economic has this field called rational expectation. They really concern themselves with these specified models. And machine learning, I would think that at least goes back to the 70s. People talk about algorithmic stability, which is actually a particular form of jackknife, goes back to the 40s. And you also have Ward in the 30s, I think, a particular Alexandra work goes back there. And Leo Brahman had papers on instability, and I think it's driving force for bagging. So all of that is really answering this question, addressing or studying or robustifying things. And I don't see statistics and machine learning as a separate fields for many years already. I feel they feed on each other, and really it's the power of integration, I think, make it powerful. And my group at here, we have been adding stability to principles of machine learning. We call PCS, predictability and computability.
So I would say robustness is a very classical topic in statistics. It's been around for several decades already. People like Hampel and Huber and Rousseau and many others made a lot of contributions. It's kind of the idea that we want our methods to do well
Says something wrong.
well.
Out of time already? We want to do...
That's an example of something unstable.
It's a perturbation.
It's a perturbation.
It's a huge perturbation.
positive.
It's a stress test, I think.
See, Richard, I told you I wouldn't let you talk.
Yeah. That's what you said. You set things on fire.
I know, it's a causal inference, I think. You caused it.
That's a great example of ironic.
Okay, everyone, we're going to start again. We're going to eat into your lunch, but there was a little slop anyway. All right, Ryan, you're on.
Okay, welcome back. There's some joke here about that fire system not being robust or stable. You can fill in the blank. Richard, you were in the middle of saying something, so I'll let you maybe start from the beginning.
Careful what you say.
Okay, thanks very much. Well, I have to say I'm impressed. It normally takes my students at least 3 minutes before they start getting so bored they hit fire alarms when I speak. I think it's what Emmanuel would call a false positive. Yeah, okay, so I was talking about robustness being a classical topic, and the idea that we want our procedures to have good performance for a wide range of data generating mechanisms, and related to that is that I don't want any single outlying observation or a small proportion of corrupted observations to influence my estimates too much. So there are ideas like the breakdown point, which is how much of your, what proportion of your observations can you corrupt before your estimate becomes arbitrarily bad. So the mean would have a breakdown point of 0, a median would have a breakdown point of 0.5, for instance. And then another popular model is Huber's contamination model, where people ask how your procedure does when you allow a proportionate epsilon of your observations to come from some arbitrary different distribution. Stability, I think, is quite closely related, but a little bit different. My thinking there is it's closely related to what Bing was talking about in data perturbations, and somehow the feeling that the effects I trust are the ones that I see very frequently on many different perturbations of the data. So it may often be the case that I can aggregate the performance of a procedure over lots of different perturbations. Maybe these are subsamples or bootstrap samples or random projections of my data into some lower dimensional space, or adding artificial noise to my data, or in Emmanuel's world it would be creating knockoffs. These are all ways of perturbing my data, and I feel like the aim here is to be a little bit less model dependent in the way that we're behaving. So that seems to be one of the goals of stability. And there was one little additional part about how different is it between statistics and machine learning. I'm not so sure how well I'm qualified I am to talk about this, but it seems to me that in statistics we often tend to work with random corruptions with Huber's contamination model or something like that, whereas in machine learning people talk a lot about adversarial corruptions. I think these are both perfectly reasonable things to explore.
Yeah, so just to give like a bit of an ML kind of view of what robustness means, so I guess it might be the most useful to actually like even like think back at how it started or how it exactly this topic gained prominence, and kind of this was this realization that like maybe like a 4 years ago, that essentially yes, we have these great classifiers that seem to be doing amazing things. However, as much as they are doing amazing things, the predictions they provide, even though they are good on average, they're actually extremely brittle. And kind of this, one of the examples are these adversarial examples where you can just take, let's say, a picture of a pig that looks like a pig to a human, and the classifier recognizes a pig, and then you just can change it in a very tiny way, just changing each pixel only slightly, and suddenly the classifier, like to us, it's still the same pig, but the classifier believes it's an airplane. Right? So I usually, of course, make the jokes about AI being so powerful that it can make pigs fly. But of course, when you at first it is amusing, but then you think about it. Okay, we are using this vision system in our self-driving cars, and now if the vision system is such that just small tilt of the scene might make it not see the pedestrian in front of it anymore, then it becomes very serious and very acute issue. And essentially, like once we realize that this is something that we really, really don't want, we have to think back and saying, okay, why do we have it in the first place? And then we realize that the standard notion of generalization in embracing machine learning of like minimizing the population risk, that essentially you want, if there's a distribution, and if you sample from the distribution, you want the loss of your classifier to be small on that sample, that this is not enough, because it does not tell us anything about this brittleness. Because usually these perturbations, they are of essentially measure 0, so essentially this is not changing the expectation in any important way. So that led to a kind of definition of robust generalization, which essentially says the most obvious thing that you would think of is saying, okay, now when I sample a sample, I don't just look at the sample, at the classification of the sample itself, but also I look at its classification for all possible perturbation within some well-defined perturbation set of small perturbations, and you measure the worst case over that, and that kind of the prediction on that you would like to be good in expectation. Okay, so that's essentially where it started, and that's what classically robustness in ML means. Of course, since then, we realize that there is many other things that are broken with machine learning than just this particular prediction inference time attacks. And somehow, just to kind of compare it to what happens in statistics, I feel we are kind of converging as a field on the same track. In some ways, statistics is way, way, way ahead of us, but kind of tracks seem to be converging because now we realize, okay, there is this whole data pipeline, and there are data poisoning attacks, there are all these things that where robust statistics is at least part of the answer. So there is a lot of convergence. And also, I might say that there was an additional realization, and this kind of is in tune with what Emmanuel has said today in the morning, is that currently, I think these problems with robustness led to some kind of identity crisis for ML. At least in my opinion, because we started to realize that it's not only about how to make our classifiers learn, but actually what it is that we want these classifiers to learn in the first place. Because we realize that the way our current models succeed is very different than how we as humans envision them. And there is some very nice kind of understanding of trying to reverse engineer the mechanics of how models work, how to make them more human aligned, how to make them interpretable. So there is a lot of things that machine learning is discovering now, like how to find better representation of data. But I think there's a lot to learn from statistics because some of this work was already done in that field.
Well, as a statistician, I'm really happy to hear that. Particularly, statistics has been way ahead of machine learners. I'm kidding.
In this aspect.
Well, not really kidding, but seriously. But let me define the. Let me give a very precise mathematical definition for me in terms of both robustness and stability. Then I'll talk more being more sort of philosophically. To me, is about the derivative is small. Whether it's a black box, whether it's however you define this more general concept of derivative. As you all learn calculus, you know what the concept means. That kind of rate of change is small. And now, for me, as Richard also mentioned, the robust notion was a notion that in statistics for a long time, and it was initially more put together as a notion to guard against model misspecifications. But for those who understand that literature, that at that time there was a pretty big debate about whether these robust methods are really good, because it could be that these outliers are actually the real discoveries, and often that is the case. So you see that, but there's no free lunch, right? That's the whole issue of doing machine learning or statistics or any of those things. So for me, I think that both notion of robustness and stability. By the way, stability to me is a notion more coming from the sort of the computer science, the computational algorithm, the iterative algorithm being stable. That's the notion that as I learned. But for me, that I think if you think about the big picture, both the robustness and the stability is pretty much everything we do. If you look at what Emmanuel talked about today, when you have a black box, you want the black box to be very sensitive to the right signal, because that's what the predictive power comes in. But then you want it very robust to the wrong signal, right? So the whole notion of it depends on, that's all of us have a job to separate the which is which. And, but I want to specifically talk about one specific example, which I think will be a really great example how computer scientists and statisticians and others will work together to address this really big problem coming. And as many of you, that this notion of differential privacy was created by Cynthia Dork and others from computer science, which has been incredibly important because protect privacy is such an important issue in this digital society. And it has become such an important tool that the US Census Bureau has announced for the next census, 2020, all the data released will be with the differential privacy protection. Now, on one hand, this made a lot of people happy because our data be private, so on and so forth. On the other hand, there are a lot of social scientists particularly gets very worried. So now it would be, I know Bing has been worried that as well. Now we're going to analyze all these data as basically you tell me that no data will be real data. It's all with noise infused. The notion of differential privacy itself is defined according to a robustness stability. That's what actually I talked to things here. That's why I literally call differential privacy. Essentially, it's saying if you, whatever system you have, by taking out one person, if the change you can see is very small, then that's protect that person's privacy. So essentially, it's a very stable with this one removing. But then, of course, when you really implement this thing in this whole sensors, there are a lot of implications because you're doing that by adding noises in a controlled way. And later, when we get to talk about applications, I want to say specifically since I got involved about how do we really think about this big trade-off between privacy, which is a form of stability, and the utility, the accuracy of the scientific results, which is actually you don't want a stability. You want have very sensitive signal to the things happening in sort of disease, prediction, all those things. So that's the fundamental trade-off, and I think that's a very exciting area that we should all get into because it's 2020 census is coming next year.
Okay. Perfect segue. Thank you, Xiaoli. So next I want to discuss whether or not the definitions that we all just talked about, the kind of the foundational ideas behind robustness and stability, are really aligned with what we should care about practically, and to discuss whether or not there are things about practical issues that should make its way back into the foundations. So people are welcome to discuss examples in their own work or in other people's work.
Okay,
Go ahead.
Okay, I can start. So, the answer is that essentially, almost by definition, what we can mathematically state precisely is never exactly capturing what we need in the real world. It's always trying to chase the concept that we have. And I think in the context of ML robustness, this seems to be even more true than in other contexts. So in some ways, again, when we say words like robust and stable, we have an intuitive meaning of it. Or even if we think of a word generalization, we have an intuitive meaning of it. But actually, when you look at what we try to put in words, you realize that this is not capturing much of our intuition. And exactly this is exactly what happened with standard population risk minimization, was not capturing this kind of intuitive robustness criterion that we as humans thought was obvious. And now, even with the robust, generalization definition, well, you have to ask a question, okay, what kind of perturbations you should be robust to? And again, there are some obvious ones for images. Yes, changing each pixel by a little one, clearly you should be robust to that. But then there are rotations, then there are local transformations, and all of that is not really kind of captured currently and not really explored from this point of view. And also, as I said, this whole notion and intuition of robustness is kind of trying to, what does it mean to generalize? There was a whole panel at ICML yesterday that I was speaking in, where there was a question like, what does it even mean to generalize? And that's kind of a question that, we don't have time to go into, but it's actually very interesting and leads to quite unusual conclusions.
So for me, actually, my interest in stability came very much from doing interdisciplinary research in neuroscience. We're working with Jack Landslide. We have this very well published work to reconstruct movies from fMRI signals about 7-8 years ago. And then I wanted to do some science, right? It kind of goes back to what Shirley was talking about. Now there's a name we call scientific machine learning, that is really you try to get knowledge out from this, I would say, a predictive, we can call engineering exercise. And the thing is how to interpret. And at the last step of this pipeline from basically Gabor transform and linear model, Lasso, then I want to interpret. And then if you change the data by 10%, it was kind of arbitrary how long they recorded this fMRI experiment with people watching clips of movies and measure fMRI signals. And then the selected parameters, like a feature, to change a lot. So that's kind of the beginning. About 10 years ago, my interest in stability is really for interpretability. And I think wrapping things around black box definitely useful, but I also think for scientific research, we need to make the black box gray or transparent, and that's through interpretable machine learning. And in terms of where we are now for my group, we're really now seeing stability as a very much unifying principle from problem formulation. You have linguistic stability, you have to worry about with multidisciplinary people work together, right? Do you mean the same things in matrix? I was talking to a biologist at IBL. For her, matrix, in her theory of cancer research, it means a biological substrate. And for me, matrix means, a matrix. So over dinner, I tried to talk to her as Mina Bissell. We couldn't really quite get across. I think I never was clear to her that I was talking about different matrix. It was a very short time. So I think from right there, and then for data cleaning, that's something I think one of the panelists mentioned, that the buts, right? Would you remove things? And that's something we really have a formal way to address as a community. How can we make that step transparent? And also we know that there's a lot of human judgment calls that we make in the whole data science pipeline or life cycle. And so we try to use what's called PCS, documentation, predictability, computability from machine learning. It's really integrating the two with stability, as for stability, and really get people to record why you make these choices, how do you connect the data. And in bioinformatics, it's very common people have multiple ways of cleaning the data. How do you make the choice? So really try to make the whole process as we practice. It's not just hardcore engineering, mathematics, statistics, computer science. There's so much I would call liberal art type of judgment calls. Can we bring that type of persuasion, or I would call empirical rigor, into the whole process? Just recognize that we're not 100% rigorous. And the documentation, I think, is an important part, not just code, but also the decision making, that to put it together. And through integral machine learning, I think will really bring the whole enterprise forward to especially what Emmanuel called mission critical applications.
So I'd say that we're quite used to being able to adapt our definitions according to what we can actually say. So to give you a concrete example, I was working on a problem of log concave density estimation. And I found that if you corrupted the true distribution with another distribution that had a finite mean, everything worked beautifully. It's all really nice, did just what you want. But as soon as that corrupting distribution didn't have a finite mean, you're dead. You couldn't use the procedure at all. So I could either report that this procedure was not robust, or I could change my definition and say that it was robust provided you corrupt it with a distribution that's got a finite mean. Which do you think I'm going to do? I think that's kind of how we often work. We often adapt our definitions, and we try to make, as long as we make clear what statement we're making, I think that's kind of okay. But it is still useful to have these kind of broad definitions, and I think either working with a random contamination model or an adversarial one, these are both quite natural definitions, I think, to work with, and definitely both have a contribution to make.
So I wanted to continue to talk about this particular project that involved on differential privacy with US Census Bureau, because I think there's a lot of really interesting stuff. I want to engage both the computer scientists, the machine learners, and the statisticians, everyone, because this is once the Census Bureau released data with differential privacy injected, you will see all kinds of data out there, and you really should pay attention and should help the researchers. And this is why I mentioned at the beginning that I'm the founding editor of the Harvard Data Science Review, because I'm getting involved in this project through this journal. And I want to give a shout to, this is a part of the Harvard Data Science Initiative. Its co-director is here. David Parks is sitting there. David is going to be a fellow tonight, right? Congratulations, David. But let me say specifically what this project is. I don't know how many of you know that Census Bureau, United States Census, they have this policy that their data are private for 72 years. But after 72 years, they can release. So what they have done is they have released 1940 census. So now 1940 census is out there, and many people probably don't know, they just recently released the code they're going to apply to the 2020 census to make the thing differentially private protected. So now any researcher, you can do the following. Take a 1940 data, analyze in a way whatever you like to analyze. Then apply the same analysis methods to the differentially private protected data. Now here the question is really a stability question. You want to see how much changes are there. For most scientists, most social scientists particularly, they want to see as little change as possible. They're worried about the impact of this differential privacy. On the other hand, you know that if there's really not much change, the Census Bureau has not done a job. It was wasting time to do all those things. You will see there were big changes. So what we're doing, teaming up with Census Bureau, is we're organizing 2 sessions for this annual conference, which is the Harvard Data Science Initiative Conference, and I was given 1 day to organize the conference. We organized 2 teams, social scientists working independently. They will be both applying their methodologies to the 1940 data without differential privacy protection, and 1940 data with differential privacy protection, and to see what's going to happen. I tell you that we are all very worried, particularly the person who's in charge of the census operation. We are really worried because it could be you will see that, and we know as a statistician, and I hope most of you would have the same intuition. What's going to happen most likely is that a lot of significant results will become insignificant. Now, for many of you, people say that's a good thing. After you see Emmanuel Candace's presentation, a lot of this statistically significant one probably should be significant. But on the other hand, you have to worry about, do we understand? Is this caused by the differential privacy protection, or it really shouldn't be significant, right? Now, so this will be the comparison we'll be doing. I just got a reminder very recently, there should be a assertive comparison, which is really the right one to do it. That requires lots of new methodology. Once the data are released with differential privacy protection, you shouldn't analyze them as if they were not protected, because you know there more noise gets injected. And the Census Bureau will tell you, they will actually, for transparency, they will tell you what privacy protection they actually provide. You cannot re-engineer that, at least statistically you can. So the really right thing to do is analyze the differential privacy data with new methodology, taking into account that kind of protection, and then compare to the ones that your original method applied to the original data without the protection, and that should be the right comparison, at least the one important comparison as well. But we should do both comparisons. The first one is really to show how much damage or how much stability is there if I don't make any changes. The second one requires a lot of new research. In fact, when I thought about it, I said, oh, this finally is going to bring back a lot of robust methods. In statistics, for example, for years we have this methodology developed. For example, trimmed means. When you take an average, don't take an average of everyone. You cut off the 95%, the top 5%, the bottom 5%, and you do those things, right? And most time we don't use those things because these methodologies are, they are useful, but we find sometimes they lose efficiency. What's interesting to me as a researcher now, I realize when you have these differential private data, these are robust methods. Not only they is more robust, they actually gain efficiency because they're going to rule out these noises inject into it by these protections. Now, how to get that done? There's a lot of work there. But what's interesting is that's a really very concrete example, and I think we should really pay attention because once the Census Bureau released those things, the impact is tremendous. Let me give you very quickly that example. The whole idea that you can take a sample, learn the population, was a revolutionary idea in the early 1900. It took 45 years to become the sort of a common methodology for social science. You know where that thing comes from? In 1945, U.S. Census Bureau decided to do sampling. And after that, it just changed the landscape. And this is going to happen next year. When they decide to put all differential privacy there, it's going to forever change the landscape. Many of us are worried, many of us are excited, but that's a great research opportunity, literally in the field of stability versus instability. So I encourage you to work on that.
Maybe I'll just add one more comment. So actually, my group and collaborators have been really successful adding stability on top of machine learning. So we arrive at something called, for example, iterative random forest, that basically adding stability to random forest. And there we have success to find gene high-order nonlinear interactions, and we have some recent right from biobank data as a test case of working on trying to predict somebody's hair is red because there's a lot of well-known genes. And talking about stability, just another level at the human interaction is that when we confirm a hypothesis with domain experts, I think we also need some perturbation there. We should give them not just the results we have For this, we actually also have like kind of fake lists for the expert to really give more authentic information for confirmation than just confirmation bias. So I think, again, stability is really throughout the whole data science lifecycle, and it's a good conceptual consideration with many manifestations the user can really adapt to their particular applications.
All right. At this point, I'd like to welcome some audience members to ask questions. Please don't feel shy. Stand up and ask any questions. There's 2 microphones, 1 in each aisle.
Anyone ask a question to get it one of these. Okay? All right, we're in trouble now.
I have a question, Xiaoli. I was surprised to hear you talk about trim means. Seems kind of a primitive thing, like to say, like, well, this is what we're going to do to the data because we're worried about outlier or whatever, like kind of Stone Age. Like, can't you just? I would think we'd want to model the distribution of these survey responses, which I guess is what the census is, and like once modeling it, you'll do inference using some approach, and whatever approach you're doing, if your model allows for various errors that you want to be robust for, then that will come in naturally. I would think that would be a cleaner approach. So I don't know why you'd want to go backward in that way. It bothers me a little bit.
Is a graduate school debate continued?
You know, for those who don't know, Andrew and I, we were twins academically. We had but so whenever Andrew talk about, I know I'll be in trouble. But this one I do know how to answer. And because you really have to think about, we're talking about all kinds of users of this differential private data. If someone like you and many of your colleagues, many of us, we can do much more sophisticated ones, taking into account how the privacy was designed, build that into the model. That's what we'll be doing. But on the other hand, that for a lot of other people who I would rather them to use some kind of a simple method, but protect them a little bit instead of just completely ignore the fact that these data now have differential privacy built in. So it's really for the practical purpose. But your call for much more sophisticated analysis, I'm all for it. Thank you. Yeah.
Can I just chime in? I thought it really depends on what you want to do with the data, right? So if you want some average, mean type of thing, yes. But if you want more sophisticated questions, definitely you have to move away from the trim mean.
Yeah. But most survey answers are essentially to average. If you know the survey literature, you will go there. Most people estimate is some kind of population average. You can write that way. Yeah.
I have a question. So when we think about deploying a model into the real world after it's been trained and so forth, oftentimes the real world changes. And so I just wanted to ask your thought on the discussion now in terms of stability, robustness, how to think about stability, robustness, or other topic in the context of changing world.
Yes, so that's difficult because in the end, that's what we really are trying to do, right? Because for that, like you have to be precise about, okay, so I think that is the biggest challenge in ML currently is exactly like how to do, like this is called like domain shift or distribution shift, how to train models that actually fare well under distribution shift. And I think, the problem is that we don't have good data sets to test it. Okay? You can, of course, deploy things in the real world, and then usually what happens is like every kind of use case has specific distribution. Maybe it's not a well-specified distribution, but there is a way you use the model, and then people essentially like they start with something, then they deploy it, and then they tweak it, so it works the way we do. And again, what is nice about notion of robustness, that it kind of provides you with a principled methodology to do a bit more better than that, than just saying, okay, let's deploy the model and see what goes wrong and just like, fix it. And essentially, so what we discovered recently was that actually, by insisting even for images, for a simple robustness where you kind of try to make sure that small pixel changes do not change the prediction of the model, actually you end up with essentially what really are happening is you are changing the prior of the model. You're embedding the prior of the model and make it more human aligned. So it turns out that you can actually fare extremely well in image prediction by using features that humans do not see and humans do not use. Okay, so just to give an example, imagine that in your dataset there is a 1 pixel that encodes this class. and you are trying to differentiate between dogs and cats. For instance, for dogs and cats, it's about the background. Usually we photograph cats inside, we photograph dogs outside, and that's actually a strong signal. The background can be a strong signal of what is the right class, but we as humans learn to discard it because we know this is not essential for the dog to cat task. The deep learning models, they have no idea. They just extract correlations, and they will use these features. So essentially what robustness does is actually provides you a way of systematically kind of preventing the model from using this kind of spurious, like meaningful but spurious features. So this is just one approach, but in the end, we don't have a very precise data sets and definitions of what we want to do. This is just an intention, and this is just it always will be domain specific.
Okay, so to keep things flowing, we're going to have to end the panel session here, so we're not too late for lunch. Let's give our panelists a big round of applause.
We still have 3 minutes.
I was told by the head.
No, you're done.
We're done.
We're done.
Thank you.
So the
We have a special order.
You can sit whatever you want, but the order of questioning is special, so you can sit. I don't think so. I mean, the order of questioning is what I said, but the order of where you sit, I don't think it matters. Where is Christian?
Yeah.
Just a little bit lower so that
is Christian?
Yeah, gotcha.
Ah, she's being wired. Okay. Oh.
Okay. You guys keep it, or?
It's so bright. It is bright.
Yeah, it's both helpful and. Sorry, my. Oh wow, you can all hear me. My mic fell off. Okay.
Okay, I guess we're ready to get going. This is the panel on fairness and ethics in data science, something that we all care about independent of whether we work on data science or not. And we have an amazing list of panelists. I'll ask them actually to just say their name and where they're from, and then we'll get going with the questions. Let's start from my left. Andrew?
I'm Andrew Gelman, and I'm a statistician and political scientist. I work at Columbia University.
Hi, I'm Christiane Lum. I'm also a statistician, and I work at the Human Rights Data Analysis Group, commonly called HRDAG.
Continuing the theme, I'm Alex Sholdoshova. I'm an assistant professor of statistics and public policy at Heinz College, Carnegie Mellon University, and I'm also a statistician.
Hi, I'm Joaquin, and I used to be a researcher. My training is in ML, and I spent the past few years in industry at Microsoft, and now the past 7.5 years at Facebook, building AI infrastructure for the entire company, and more recently, the last year, working on AI ethics and fairness.
And I'm Yannis Ioannidis. I'm a professor of informatics at the University of Athens, and also the president of the Athena Research Center, also in Athens in Greece. And I'm also the ACM Secretary-Treasurer. So let's start with some questions, and I'll start with the very title of the panel, Fairness and Ethics in Data Science. Is it mostly an issue of policy, of mentality, or of technology? Alex, would you like to take a shot?
Sure, I'd love to. In my mind, it's all of the above and then some. I think there are some things that are missing from your list. It's a matter of decision making, it's a matter of psychology, behavioral economics, all these things that we as statisticians and computer scientists don't necessarily spend all that much time talking about or thinking about and are perhaps unfamiliar with. So I want to go back one step and ask, why are we concerned about fairness and ethics right now? Like, when did this all start and what motivated it? And as Emmanuel reminded us earlier this morning, if you think back to the sorts of problems that we were dealing with maybe 15, 20 years ago, this was something like the Netflix Prize Challenge, right? So let's recommend movies. And at the time, I don't think too many people were really concerned about these issues of fairness, accountability, transparency, ethics, and the technologies that we were deploying. But now we are, and I think what has changed is that technologies are now being increasingly deployed both in the private and public sector to make decisions or assist in the decision making in settings that are of consequence to individuals in society. And so now we need to be concerned. And echoing something that Ben was saying on the previous panel, there's an important translation task that I think we need to engage in. And this is where things like policy and the decision sciences and law come in. Ben was pointing out that the term matrix means something different to a biologist than to a statistician or a computer scientist. But I challenge you to think about what justice or fairness or trust or contract mean in statistics. These are things that we simply don't usually have definitions of. And yet we are trying to propose technical solutions to these challenges that are phrased in terms of terminology that is unfamiliar to us. So I think it's really important to engage with these other disciplines, invite them to our events, attend theirs, so that we build a common language in order to tackle these problems.
Okay. Joaquin, do you want to say something about it?
Yeah, absolutely. It's funny because of the questions you proposed, this is the first one that caught my interest, because the hardest lesson that I have learned, and most interesting lesson that I have learned the past year, coming at the question of ethics in general, but I'm going to talk about fairness specifically, was that I've realized without a doubt that it's a way more complicated problem than I thought it was, and one of the key ideas that I'm obsessed with is that fairness is a process, and that I think that many of these ethical questions are processes, and these processes should include key steps. One is to make sure to systematically surface all the hard questions, right? And I'm going to give you a couple of examples for fairness. And then to have systematic processes to resolve those questions involving all the right people. And most of the time, if you're thinking about AI bias or algorithmic fairness, you will actually not want the AI practitioner to be the person making the decision, either because we're not equipped to make it or because it shouldn't be us making the decision. And then a third part that is really important is to have careful documentation of the decision processes and what the decisions that were made were, for transparency, obviously, but also to build, internally I talk about building case law, because many of these decisions we have to make seem unique, right? So I want to give you a couple of examples of what this looks like on the ground in practice, okay? So imagine that you wanted to build a system, you wanted to use ML to help with the problem of reducing the spread of misinformation or of false news, right, on a platform like Facebook or like any other sort of web sort of platform, right? So obviously, initially you could say, well, why don't we use professional fact checkers, right? Like that's one possible approach, right? That doesn't work because the scale of the problem is pretty massive, right? And then you have additional challenges. The definition of what constitutes false news isn't clear in itself, right? It depends a lot on the point of view, right? And then finally, professional fact-checking is a process that takes a long time, right? Okay, so now you're an engineer and you're thinking, all right, well, what can we do, right? And you're trying to build this out. And you think, well, here's a research project, and this is an actual research project we're conducting at Facebook, which is like, well, could we ask members of the Facebook community to try to point to journalistic sources that either confirm, or contradict a claim that's being made in a piece of content, right? And when you think about that, you have a lot of hard questions that start to arise, right? Like one is like, well, who are those people going to be, right? Is it all going to be like members of the Facebook community who live in the Bay Area? Well, how is the rest of the country going to feel about that, right? Not to mention if you try to do this in other countries, right? So obviously, when you think about fairness, you have to be thinking about what are the dimensions that I should be considering, what are the important groups to think about. Your AI engineer, me in this case, should not try to answer those questions, but there should be a discipline to ask those questions, right? So obviously, this is something that we're tackling. We're looking at things like geography. We're thinking about gender, age, and we're thinking about even like political ideology, to make sure that there is a diverse representation there. And that's just the labeling process, right? But even before that, right, like you need to stop and say, well, content moderation, right, is about trying to protect the community from harm, but what does that do to freedom of speech? And are there groups in society, you know, whose ability to express themselves might be compromised because we're trying to do this, right? That's not an AI question, but it is going to be a very relevant question in how I actually build my algorithms, right? Another interesting example is the India elections just took place. 900 million people voted, the biggest elections in the history of humankind, right? And in there, obviously, we were very, very nervous, as you can imagine, right? Because there has been a lot of election interference happening on our platform, right? And so we had you know, another interesting example on the ground, right, of a fairness question is, there again, you know, although we partner with election monitoring organizations and so on, it's very difficult, right? It's impossible to review everything, right? So you need to prioritize. And so there's a very beautiful symbiosis and collaboration between, you know, ML, which prioritizes the content that humans should review, right? And then humans, professionals who are reviewing that content and making decisions, right? But India is a very diverse country. And so then you think, well, if I think about fairness, what if for some regions in India or some languages, right, I don't have enough data or my algorithms are biased in some way and I'm either flagging too much content to review or not enough, right? Then I'm not optimally allocating my limited human review resources, right? So there was another practical on the ground, you know, fairness question we had to ask. But again, we had to sort of pause and say, well, what are the hard questions here, right? And it was things like, well, what are the most sensitive groups in that country? You know, I have no idea, right? So you need to work with the right people in the country, right, to answer those questions. But very quickly, you realize even that, I'm just going to say something uncomfortable, that many of these questions end up being political questions. And I think it's important to feel comfortable with the reality that if you're reasoning about algorithmic fairness and you know, issues of ethics in AI, you have to escalate some of these questions all the way up, right? And they're going to be very uncomfortable, and the right people inside and outside the company need to be involved. I'm going to try and wrap it up with I had a lot more, but I want to be conscious of time here. One of the things that I'm really excited about is to see that both in academia and also in industry, that there's an emergence of very multidisciplinary teams. Traditionally, you know, at Facebook and at Microsoft, I've seen teams like policy or, you know, legal almost as the enemy. You know, you're trying to build this thing, and then you're like, oh, God damn it, I have this checkbox that I have to take with the policy team and with the legal team so I can launch my product, right? That does not work, right? That does not work if you're trying to answer very difficult questions like these. So right now in my team, we have moral philosophers, we have political scientists, we have artists, and I think you mentioned some disciplines that we don't have in my team yet, but I'm really excited about this. And then in talking to friends, you know, in academia, I'm seeing, you know, departments of philosophy and departments of computer science building joint programs, and I'm extremely excited about this, and I think that's going to be really important. And I'd like to quote someone that I've been talking to, Sandra Wachter, who's at Oxford, and she's been studying things like explainability. You know, she comes from law, so she comes from a different perspective. And she said this one thing to me end of last year that still resonates, right? As we were having these kinds of conversations, she said, you know, many of these questions of fairness, you know, we've been debating them since Aristotle, right? So it's been a long time, and we haven't resolved them yet. And she says something like, it's really important that we don't burden technology with difficult issues that we humans have not been able to answer.
Okay. Well, I may come back with some of the aspects that you brought up, but let me go to Andrew. Andrew, we talked about bias and algorithmic bias. What are some ways in which you can think about algorithmic bias as a social problem and not as a technical problem?
Well, I guess first I should say that when I think about ethics, it's usually about like something bad that somebody else has done. But maybe we should think about bad things that we've done. So I want to talk about an ethical failing of statistics as a field, or machine learning for that matter. And I think that it's that we sell statistics or quantitative analysis as a way of converting uncertainty into certainty. And in some settings that makes sense, like if you run a casino in Las Vegas, you really can convert certainty into uncertainty, or uncertainty into certainty, because there you have a mathematical model that's very accurate. But in other cases, that's not the case. I think what we teach is that identification plus statistical significance equals truth. And we spend a lot of time focusing on little problems, or like the implication is, well, we figured all this stuff out. If it's statistically significant, it's true. If you have causal identification, you can believe it. And then there are a few technical things we have to worry about extending it to other problems. But I don't really know that that's the case. And we also teach that if you have a randomized experiment, all you need to do is increase n, and you'll resolve all your problems. Because after all, life is bias and variance. And if you have a randomized experiment, you have no bias, and the variance goes like 1/square root of n. But that's not really right for two reasons. First, you can have bias in a randomized experiment. It's the people in the experiment can be aware of what's going on in the experiment. And also, effects can vary by person, so there can be bias based on who's in the experiment or who's still in the experiment. Second, you don't really increase n because you're only increasing n of the sort that you're getting more measurements of. You're not learning about other scenarios that you might care about. Now, here's the problem to me is that there's a distinction between evidence and truth. And I think a lot of people feel that if they know the truth, well, let's say if you know the truth, this can motivate you to go beyond the evidence. And when there's the expectation, I would say right now in science, there's the expectation that a good study, a high quality study, should yield statistically significant results, or the equivalent near certainty using some other method. The problem is not with a p-value or statistical significance. The problem is with the expectation of near certainty. Now, when you have that expectation, first there's a pressure to cheat in some way to produce the certainty that's expected of you. And of course, there's selection bias that the cheaters can prosper. Conversely, the expectation of certainty can lead uncertain results to be taken as zero. And again, if you look at statistics books, including my own, we go through lots of examples where, oh, we had a question, we gathered data, and here's the result. The 95% interval excludes zero. There's the false positives have gone away, whatever it is. So the expectation is that's how science is supposed to proceed. Right? Now, that's not true in other areas of endeavor. If you do sports, I need hardly to remind people in this area of the country that you can lose sometimes, and that's okay. Sports would be pretty boring if you won all the time, wouldn't it, right? And so the expectation is that you do better, but in science, often the expectation is that you win every time, or more subtly, it goes like this. Somebody does a study, they think they have 80% power, maybe a third of the time they succeed, and so they feel very virtuous that they've taken the hit. They've taken the hit 2 out of 3 times, but actually their studies have 5.1% power, and almost everything they're seeing is noise. But they feel like they've worked so hard for their successes, they don't want to let go of them. Beyond that, lots of overconfidence followed by embarrassing scandals can rightly reduce our overall respect for data science and data engineering. In summary, I think the algorithmic bias that concerns me is not so much a bias in an algorithm, so much as a social bias resulting from the demand for and expectation of certainty.
I like what you said, that if you believe you know the truth, then you can ignore the evidence. That's the way, I guess, many world leaders operate these days, and we see the results. Okay, we talked a lot about algorithmic bias, but there is also the data bias. I mean, data bias versus algorithmic bias, how do they interact and how do we avoid them or compensate for them? Christiane, do you want to?
Yeah, so actually I think this ties back to something Alex was saying a little bit earlier about some of the complexities around around the terminology we're using. So I think for many of us in this room, when we hear the word algorithm and in the context of, say, predictive modeling or something like that, maybe what we're thinking of is the set of computer instructions that tell us how to estimate the parameters of the model or something like that. By and large, I don't think that there are any cases where someone has sort of fiddled with that aspect of an algorithm to result in some sort of bias that we think of. I don't think there's some sort of malicious actor out there, or I haven't seen examples of malicious actors out there who are, hard coding into something like if person equals minority, then treat badly, or something like that, right? That's not how this is really working. And what that sort of leaves in terms of the bias is the other aspect of it, sort of the models that come out of taking your algorithm, learning parameters from data, and then producing a model. And so coming back to the terminology, I think in sort of the common discussions you'll be hearing in the news media, often what people mean when they say algorithm is that. They mean the model. They mean sort of the fitted parameters, the way that you, say, count up the points on your fingers that someone gets against them, like 2 points for being young, 3 points for having previous arrests that sort of will make predictions about whether they'll be rearrested again, for example. And so there is that sort of divide there. But my opinion is that most of the bias that we're seeing comes from the data. It's derived from the data. It's that the algorithms are learning from the data these patterns that reflect bias. So I think it's worth diving into a little bit what we mean when we say bias in this case, because I think there are many statisticians in this room. I think we're 3 out of 4 at least on this side of the panel here. And so probably what that means to many of us is something like selection bias or sampling bias. And I think that is a legitimate use of the term in this case when we're talking about biased data. So one example I usually go into to illustrate how that might lead to a biased algorithm in the sense that we hear about when we're talking about this in sort of popular discussions is using police data to make predictions about who will be a criminal or who will be arrested in the future. So the idea being, for example, if you were to have police data on, say, on drug crimes, for example, there's this reality that in the United States, drug crimes have been disproportionately enforced in communities of color. And then so if you use that data to learn patterns in that data to then make predictions about, say, where you'll likely find drug crime or who will likely be arrested for drug crime in the future, you'll sort of perpetuate those problems. You'll be over-predicting, you'll be disproportionately predicting in those same communities where the data itself is reflecting this historical over-enforcement. So that's one aspect, right? That's sampling bias. The data is more likely to contain drug crimes committed by people in communities of color than other people. That's sort of definitely what's going on there. I think another example of bias we need to think about is measurement bias, or sort of these types of representation. So where there's sort of systematically different representations of one group versus another group, or one individual versus another individual. And the example I like to go into here is teaching evaluation. So what we hope they measure is something like teaching efficacy, right? But there have been studies recently that show that even if an instructor, so it is the case that female instructors, at least in these studies, and male instructors were equally efficacious when measured using more objective measures. So how the students performed at the end of the year on the exams that were consistent across the different sections, or how long it took them to return the exams, something like that, where you can really just get an objective measure of their performance. However, when you look in the teacher evaluations, the student evaluations of the teaching, what you'll see is that female instructors were systematically ranked lower than male instructors, even for the same level of performance in terms of the objective measures. So then if you were to make a model based on that data, right, we have this sort of systematic bias against the female instructors in the data. It's not that some instructors are missing from the data set in a way that's not random. It's not sampling bias, it's this measurement bias, where the data itself is reflecting the biases of the people who are evaluating the teachers. Then if you were to fit that model, right, if your model's any good at all, even if you don't include a variable like gender, what will come back is that, conditional on whatever covariates you're able to collect about the instructors, you're likely to find that the model will recommend or will predict that female instructors will be less efficacious if you were using the teaching evaluations as the measure you're trying to reproduce. So that's another example of bias, and it's something totally different than the sampling or selection bias in the first case. The last example I think that we need to think about as well is cases where the data is measuring reality perfectly, but the reality has come about as a product of some sort of inequality. And so this example I'm going to give is a little bit silly, but it caught some attention in the media. And it has to do with what happened. It doesn't happen anymore, thank goodness, but what happened when you Google image search the word CEO. And you can probably guess what happened. What came back was a page full of men, right? Like just sort of what probably many of us envision when we think of the word CEO. And this reflects the reality that CEOs are more likely to be male than female. Of course, it was an exaggerated version of that reality. The ratio was more imbalanced than it appeared in the real world, but it did reflect some sort of underlying inequality in the world. So there's that issue. I mean, in this case, it was a little bit more egregious in the sense that the only female that appeared on the first page was CEO Barbie. Google has then gone back to fix that, thank goodness. And so, that's a different representational harm that we need to talk about, but that's sort of not illustrating this other example I'm talking about where, there is this sort of underlying true inequality in the world. The data is measuring it accurately, and then do we want the models to reflect that inequality? So then this gets back to, what have been some solutions for algorithmic solutions to these issues? By and large, I think some of my favorite solutions have been less in the vein of saying, hey, the data is wrong, so much as saying what the right thing to do is to, say, limit the extent to which this algorithm can impact this community versus this community. So that's to say, to limit the impact, to limit the rate of false positives in, say, black versus white to be the exact same. And our very own Alex here has proven that under various circumstances where the distributions truly are different in the two groups, you could end up with sort of counterintuitive situations where you're doing very well in one predictive measure that intuitively seems very fair, but then you'll end up with these other, when you look at it through a different lens of fairness, sort of something, say, like false positive rates should be equal among groups, that you can't have both at the same time. And so I'll close really quickly. That vein has sort of been building values into the objective function that's used to learn the model. That's sort of what's going on, right? You're saying, okay, we value having the false positive rates be the same in this group versus this group. That's not really a statistical decision, that's a normative decision. And so, I often hear, like, why are we building values into models? It's statistics, it's science, it should be neutral. But just because you choose some sort of, say, some estimation procedure that's off-the-shelf software, doesn't mean that you're not building values into it. You may be building in values that you're not aware of, but you are building in values. Perhaps the value is that an error in this group is the same as an error in this group, right? But you actually are building in values. So just because it's mathematically convenient or software exists to fit a model doesn't mean that there aren't values encoded in that itself. So I think a lot of what we're getting here is we're getting away from the idea that the data itself is neutral and that the decisions about how you model that data are neutral.
Andrew, you wanted to add something?
Well, I just love that point. And of course, in social science, we talk about utilities. And the term utility is funny because it kind of sounds neutral. But obviously, social scientists have thought a lot about different people having different utilities. And in computer science, we use the loss function. It's the same issue. So I agree. I also thought, like, the example of the CEO is interesting because it reminds me of a well-known math problem of the probability matching versus prediction. So if you have a deck of cards and it has 90 red cards, or let's say 70 red cards and 30 blue cards, then you should, if you want, each time if you're supposed to predict whether a card is red or blue, you should say red, 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 because that's, but of course that'll make it the aggregate prediction be wrong. And that indicates an issue that when we look at our loss function or our value function, or if you want to be more positive about it, we might want to put a value on the aggregate. And so it's a math problem, which is good, right? I mean, that means that some of these problems can be addressed at a more technical level if we step back and think like social scientists and ask the question carefully. Then there really is a potential for a lot of our technical ideas to make contributions, as long as we're not too limited in what we look at.
So why are so many predictions of automated decision systems wrong? I mean, we have it in election campaigns, we have it in recidivism, urban homelessness, loan default, and so on and so forth. Is it only bias? Alex, do you want to say something about that?
Sure. No, but that's not the end of my answer.
Good.
So I think Christian pointed to some really important points that need to be emphasized in any curriculum or really any collaboration that tries to speak to policy applications or consequential decisions, which is this idea that our standard framing of these sorts of prediction problems, which say predict Y as accurately as possible according to loss L is very limited. So I want to draw on kind of two elements here. One is that, first of all, we don't expect predictions to be accurate in these contexts simply because imagine trying to predict loan default or who's going to commit a crime in the future. And you can dream up whatever data you want. None of that is actually going to be sufficient to get anywhere close to perfect accuracy on these prediction tests. These are just inherently complex phenomena. In technical terms, the Bayes error, given whatever set of features you want to envision, is going to be extremely substantial. But this provides us with an opportunity, and I think this is an opportunity that Leo Breiman would have characterized in part with the Rashomon effect, which is this idea that there are many models, and considerably different models, that actually differ significantly in their predictions, that all achieve essentially the same accuracy, that on most aggregate measures they will perform very similarly, but as far as their implications and individual classifications go, are going to be very different. Right? So we may have one model that's as accurate as another, but where the different models commit errors or how they commit those errors are going to be very different in a way that's not captured by a loss function. And I think therein really lies the opportunity. This is where, as Christian mentioned, we can actually inject other elements, other societal values into the sort of modeling that we're doing, because two mathematically equivalent or technically equivalent objects may nevertheless be perceived differently by users. They may be responded to differently due to different psychologies. They may be perceived differently under the law. And the other thing, so the other thing I'd like to mention here is that as we think about, I blanked on this. Give me just a second. Right. Sorry about that, awkward, but hey. So the other thing I want to bring in here is this idea that accuracy is actually not the thing that we're necessarily striving for. And this is kind of illustrated due to the following fact. We've known through research in the decision sciences, going back to the pioneering work of Paul Meehl in 1954 and the follow-on work of Robin Dawes, again from the 80s, that even simple statistical models will outperform humans on simple prediction tasks. So if you ask doctors, will this patient be readmitted to hospital in the next 6 months? The doctor that treated that patient. Or you ask a simple logistic regression model. Well, there have been studies that show that doctors have AUCs that are somewhere between 0.5 and 0.6 on this task, whereas you can perform much better with a statistical model. And yet, if you ask people, even given that sort of evidence on accuracy, do you want a statistical model making consequential decisions, or do you want a doctor or a person involved in this decision? Overwhelmingly, you will hear that we want humans involved in the loop. And why is that? Well, what this points to is, again, this disconnect between the simple prediction tasks on which our machine learning models or statistical models perform extremely well and the actual objectives that we have. So in some sense, there's a disconnect between the decisions that we're trying to make and reasonable basis for that decision and how much of that is quantifiable, and the sort of tasks that our machine learning models are solving. And I think if we keep that in mind, we can actually make reasonable progress by, for instance, in trying to incorporate some more of these values that aren't naturally captured with the sort of tool sets that we might deploy off the shelf.
You have a short comment on that?
I'll be very brief. I am on. Yeah, so I think, we have seen all these really great advances using machine learning and statistical, predictive modeling in areas. Alex pointed to one where humans aren't doing so well. Maybe models are doing better, but in particular, some of the most impressive ones have been in cases where humans are really good at it, right? Like, is this a cat in the image or is this a dog in the image? Like, we can do that really well. But there are some cases where the sort of irreducible error is large, and I think a lot of the cases where people are concerned about the fairness and the ethics fall into that category. So predicting how someone's going to behave in the future is one of those categories. I think it's just fundamentally very difficult and fundamentally very random. I think the other thing we need to take into account is it's not just, whether there's a cat or dog in the picture is not going to change based on what I do about it. But, I could actually intervene in some way to help a person if I say, they're going to have some bad outcome medically. There's different interventions you could make if we're talking about again, sort of the context I usually think about is recidivism prediction. So if we're thinking about whether someone's going to be rearrested again, there are interventions you can take. So the prediction itself isn't the end of the story. It's what can we do about it, right? And I think sort of the final thing, since I did say I'd be brief, is I also think that in light of the fact that in many cases we are dealing with models that aren't super accurate, right? They're not getting, they are making a fair number of errors. I think it is reasonable to start thinking about situations where technical solutions or predictive solutions aren't what we need to be doing. So having sort of the technologists take a step back, defer to the policy folks, the law folks, things like that, and see what other solutions are available.
Joaquin has a comment, but we'll then go to questions from the audience. So if you could line up behind the mics, please. So Joaquin, you wanted to say something?
Yeah, I wanted to comment on two things. One, I really like what you said, Alex, about there exist multiple implementations of an algorithm that will achieve the same accuracy, or even maybe if you care about procedural consistency, or if you care about, if the definition of fairness you care about is equal treatment, as it were. The outcome differences of different implementations that have the same accuracy and that implement equal treatment can vary a lot, and this is something that we actually have seen in practice. And so one of the things that that we end up doing is actually monitoring those outcome differences, and then all things being equal, picking the implementation that has the smallest sort of disparity there. And then another thing that I think is very important to mention is that, and I think this is pretty clear in what you guys said earlier, is there are other decisions, such as how your algorithm is being used in a broader context that can also end up impacting people in very different ways. Although at the onset it seemed like they didn't make any difference. They didn't explicitly have different policies for different groups. And so that's another thing that I think is important too, beyond the algorithm, is sort of, if the data you're collecting is a result of some policy or some guidelines or something like that, you also need to explore the space of guidelines that seem like they're all reasonable, and then test things, and sort of go measure, what policies and what guidelines seem like they have smallest impact differences.
Okay, please, question.
Alfred Spector from 2 Sigma. As this is the first ACM IMS, so Computer Science and Statistics Joint Summit on data science, it would seem that getting the definition of that term right actually is important, and not just, say, in a pedantic way. The earliest definitions I think that we heard here today were focused primarily on the technology and techniques of computer science and on statistics and applied mathematics, operations research, and focused on that. This panel is thinking about a bunch of issues relating perhaps to ownership and valuation of data, objective functions that we need to set as we use data for certain kinds of purposes, and politics or whatever, maybe behavioral implications on individuals relating to humanist issues such as free will. I don't think that came up, but it could have, and other topics as well. Do you think we should explicitly agree as a group that our definition of data science is holistic and includes these social science and humanitarian issues within it?
Who wants to tackle that?
Sure, I'll make one comment in response,
Alex?
which is that I don't think that we want to be kind of imperialistic about it. I don't think we ever want to say that the humanities are now a data scientific problem. That's really not where we're going. But I think that we need to acknowledge as a community that insofar as we are trying to kind of encroaching on territory or making decisions or kind of constructing technological objects that are having impacts or consequences in domains that are typically the purview of these other fields, that we actually need to meaningfully engage with those fields and understand the problems and potentially the problems that we ourselves are causing and the extent to which we can propose meaningful technological solutions as technologists.
Well, yeah, we have 2 more questions, so I would rather go around and then may come back. Please.
Hi, my name is Juan. I work for the International Telecommunication Union. Thank you for the talk panel, really great panel. I know there's a bit of discussion about kind of the centers of excellence, specifically bringing in people from multiple disciplines together to hopefully come up with a more holistic and common language or framework for being able to apply data science and machine learning towards actionable projects at scale. I think my question is more in line with kind of how that can be communicated across other sectors or non-digital native stakeholders who are not necessarily are not necessarily up to date with the terminology that we're using right now, specifically in a way where we can empower organizations or stakeholders who are data rich, such as I guess international organizations like the Red Cross, and enable data scarce digitally native stakeholders like someone who's a smallholder farmer, for example. Just curious about it.
Another simple question. So who wants to take it? Yeah, Andrew.
I think it would be great if we can convey uncertainty and variation. And I think one of the good things about machine learning in particular is there seems to be a real tradition of that. So even when people are bragging, they'll say we can classify this 70% accuracy or 80% accuracy, which means you could be wrong the other 20, 30%. So I think that's great. I think that machine learning is already in the right direction of that.
And you think that the Red Cross and people from these kind of organizations will be able to catch that?
I hope. I mean, I just like that. I think it's better than saying we've discovered blah, 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 right? Instead of that, it's like we can predict with this accuracy. It's a much more modest statement. I like it.
Okay, please.
Hi, this is Mohammad Hajjaqari from University of Maryland. First, I want to say, actually, I checked that CEO. There are a few women, a few women up here there. So just the first thing I searched at Google, and there are a few women up here, I think. So there was just some side comments. And the other thing that I want to say is that, I mean, here when we talk about ethics, I think there was a question that raised before, what's the meaning of the data science? So one thing that I can define essentially is that data science is just understanding the data in the past. So if we consider this definition of data science, then in some sense we should not blame algorithms for doing something wrong, essentially. So if something happened in the past, I mean, the algorithm maybe correctly finds that things essentially. Like, for example, consider people of color and, for example, police investigation or something like this. I think a better way, it might be better, I mean, consider that algorithm, don't blame the algorithm. However, I mean, the thing that we are doing in game theory, try to define some other functions or some other objectives to the utility functions, and then consider a combination of that such that in the future this does not happen. That might be a better way, I will say, and maybe more accurate way of essentially considering ethics. Yeah.
Any brief comment?
We're supposed to stop, I think.
Say it again?
I think we're supposed to stop.
I was given
now.
1 minute.
Oh,
yeah,
sorry.
yeah. So any brief comment, and then we'll wrap it up? I mean, we are wrapping it up with any brief comment by any panelist?
I disagree with the premise that data science is about understanding the past. I think that's a very constraining definition, and I think that it is about understanding the past so that we can predict the future.
Great. Okay, I want to thank all the panelists for great discussion.
Can you hear me? So lunch is upstairs on the second floor. Go up
Thank
the
you.
escalators in the atrium, I'm told. And we will resume promptly at 1 o'clock. Thank you.
Good afternoon, everybody. Please take a minute to settle in. It is my great honor and pleasure to introduce Jeff. So some important bits about Jeff. So as is customary, when we do introductions for professor, we say they're a professor at so-and-so. So Jeff is an engineer, and he's an engineer at Google. And look, I'm looking at his bio, and it looks like he did his PhD in University of Washington. It sounds like neither MIT, Carnegie Mellon, Stanford, or what was the other school they were competing over, ranking? Sounds like Harvard. Oh, right, Harvard. It sounds like they all screwed up and wouldn't take him. He moved to Google at sort of 99, the dot-com era. People were making bad decisions. He made a few bad ones, too. Since then, it looks like he's been very busy. He's been working pretty hard. And he is now a senior fellow at Google. He also heads Google's research and Google's health research in particular as well. And he's just done a couple of projects you might have heard of. So for instance, he's the implementer of TensorFlow, MapReduce, Bigtable, Spanner. And to me, the most exciting and impressive thing about Jeff is that he's multilingual. He doesn't just speak in English, he also speaks code and puns. And so the thing I've always wanted to know is, how does Jeff spend his time during the week? And what fraction of his time does he spend on writing in, speaking in English, code, and puns? And I'm hoping Jeff will talk about that during his talk. Thanks, Jeff.
Very much. Can you hear me? Oh, and I need a clicker. Great. Okay. So I'm going to talk to you today about some of the work. This mic is supposedly going to be turned on by the mic people. There we go. There we go. Okay. And I'm going to be presenting work done by lots and lots of people across Google. So this is not purely my work. It's many, many people contributing lots of different things. So first, I want to touch on the state of machine learning research in the world. There's this amazing explosion in interest of doing machine learning research. So arXiv is a paper preprint hosting service. And this is a graph showing you how many papers are posted tagged with the machine learning related subcategories in various years, starting about 2009. And the interesting thing is, around 2009, kind of our nice Moore's law computational growth that we've been so accustomed to for the last 40 or 50 years started to slow down and really hasn't been growing at the same rate. That exponential growth rate of computational power is shown by that red exponential, but it is now flattened out. But we've now, instead, we're generating machine learning research ideas instead of more computational power, and at a faster rate than Moore's law exponential growth rate has been in the past. So that's a lot of people entering this field looking to do interesting things across lots of different disciplines. And one of the really exciting areas about machine learning is a sort of sub-area of it called deep learning, which is really the modern reincarnation of artificial neural networks, which have been around for about 30 or 40 years. In fact, tonight, the Turing Award will be presented to Yoshua Bengio, Geoff Hinton, and Yann LeCun for their contributions in a very long period of time and making fundamental ideas that we're now seeing really work well come together. And what's really new is, we have a bit of new network architectures and new kinds of techniques, but a lot of the fundamentals that we're using really are algorithms that were developed 30 or 40 years ago that are just now starting to really sing in the last 8 or 10 years as we've gotten enough computational power to make them do really impressive things. And one of the key benefits of deep learning is that unlike a lot of other kinds of machine learning methods where you sort of hand engineer a bunch of features and then learn to the final weights with which to combine these sort of handcrafted features, Instead, deep learning via neural networks learns both the features and the output predictions of the model simultaneously. So it can learn from very raw forms of data. And just some examples, you can think of neural networks as able to learn really, really complicated functions. And they can act, this is not y equals x squared. This is, you put in raw pixels, and it can tell you that's a leopard. Or you can put in audio waveforms, and it can give you a transcript of what is being said, purely by training on examples of audio and what was said in that audio clip. So give it lots and lots of examples, and it can learn to generalize to a new audio clip of someone saying something completely new it's never heard before. How cold is it outside? Hello, how are you? Put in as input, and you can spit out text in another language. Bonjour, comment allez-vous? Purely by training on English-French sentence pairs that are aligned, mean the same thing. And you can do interesting things, not just classify pixels, but you can actually train these models to do sort of simple linguistic tasks from images. Can the model write a simple sentence describing that scene, given lots of training data of that form? A cheetah lying on top of a car. This is actually one of my vacation photos, which was pretty cool. So just to give you a sense of the progress in the last sort of 8 or 10 years, Stanford runs a image classification challenge every year called the ImageNet Challenge. And in 2011, that was the last year before people started using deep neural networks for computer vision. And the winner that year got 26% error. The winner the previous year got like 28%. So it hadn't really been decreasing much. And we know human error on this task is about 5%. It's basically you get a color image, and you have to give 1 of 1,000 categories to it. And it's actually reasonably difficult because there's 40 different breeds of dogs you have to distinguish and so on. So in 2016, the winner got 3% error. Right? So we've gone from computers not being able to see very well to now computers can actually see. And this has huge implications in the world. So I'm going to structure the rest of the talk around this nice list of that the US National Academy of Engineering published in 2008, which is basically they got together a bunch of people from lots of different disciplines and thought about what should we be trying to address across all of our disciplines in the next 100 years. Except they waited 8 years, so we now have 92 years to work on these things. And they came up with this pretty nice list of 14 different things. And I think if you read that list, you're like, if we solve these problems, the world will be a better place. It won't be quite so hot. People will be able to learn more effectively. Healthcare will be way better. Lots of good things. And the interesting thing is, I think if you look at machine learning today, it's going to be key to solving a lot of these problems. And so I'm going to structure the rest of the talk around how I think machine learning is going to help us solve some of these grand challenges. Within Google Research, we're actually working on all the ones listed in red, but I'm going to focus on the ones listed in boldface. OK, so restore and improve urban infrastructure is one of them. And we're on the cusp of something pretty amazing, which is autonomous vehicles, right? And if you think about if we really have autonomous vehicles on the road working, it's going to really transform how we think about building cities. We won't need parking garages. You'll just kind of summon exactly the right size vehicle to come pick you up, one-seat vehicle for you, or maybe you're at Home Depot, so you need a pickup truck autonomous vehicle to come and get your lumber or whatever. And the thing that's enabling this is the fact that we can now fuse raw sensor data, LiDAR data, camera data, and radar data, other kinds of data, and use machine learning to build a model of the world around us so that we can say, oh, well, that's another car, that's a pedestrian, that's a light post, it's unlikely to move, and then help make predictions of what actions we want to take to safely navigate the world around us. And just to give you a sense, Waymo, which is Alphabet's self-driving car subsidiary, has been running tests in Phoenix, Arizona over the last year with no safety drivers in the front seat and real passengers in the back seat. So this is not some distant, far-off thing, but we're actually driving around the roads of Phoenix, which admittedly are an easier environment than most because it's really hot, there aren't that many pedestrians, the other drivers are kind of slow, it never rains, but it is a real urban environment that we're driving around in with no safety drivers. So that's pretty exciting. Now that vision works, it's going to be easier to make robots do things. And this is just an example. one of the things you obviously want a robot to be able to do is pick things up that it's never seen before. And in 2015, the success rate on a particular task of picking up an unseen object you've never experienced before was about 65%. And one of the things we've been doing is looking at how we can use multiple robots, collect experience from multiple robots, have them practice picking things up, and learn from their experience. And using that, we were able to get to a 78% grasping success rate. And then more recently, we've been doing more sophisticated algorithms, refining our approach a bit, and we're now at 96% grasp success rate for picking up an unseen object. So we've gone from basically a third of the time you can't pick something up to you can reasonably depend on being able to at least pick something up and then string together sequences of actions to actually build robots that can operate in messy environments. Another thing we've been doing is how do you actually get robots to learn new skills rather than hand-coding control algorithms, which has been the traditional approach in robotics for many, many years. This is one of our AI residents demonstrating things to the robot. They also do machine learning code, but at the moment, he's giving us video data to emulate. And you can see the simulated robot is trying to emulate what it's seeing in the pixels. And on the right-hand side, it's pretty interesting. If you want to teach a robot to pour, that's a really complicated hand-coded control algorithm, and it would probably not work very well. But what we've done here is given the machine learning system and the robot about 15 short video clips of people pouring into different kinds of vessels from different angles. And then the robot gets 15 trials to try to train itself to pour, given the video data and its own sort of reward experience. And so with that, it's able to get to learn to pour at, I would say, maybe like a 4-year-old level, not an 8-year-old level. But it's pretty good. If you think about what's required to teach a robot to pour, that's promising. And there's all kinds of training data, like people cracking eggs on YouTube, and you can imagine training on lots of kinds of data. OK, another one was advanced health informatics. And this is an area where I think there's just tremendous opportunity to make healthcare decisions be better in collaboration with healthcare professionals. And one of the things that I think is really exciting is can we use machine learning to bring expert decision making and spread it around to many, many parts of the world that don't have a high concentration of experts. And I'll use diabetic retinopathy as one example of a particular task. So diabetic retinopathy is the fastest growing cause of preventable blindness in the world. Basically, if you're at risk for diabetes, you should be screened for diabetic retinopathy on a yearly basis. And so there's 400 million people at risk for this who really should be screened every year. And it's very specialized. You need basically an ophthalmology degree. A basic MD can't do it. And in India, for example, there's a shortage of more than 120,000 eye doctors. And the real tragedy is this disease is very preventable if it's caught in time. So but if you don't catch it in time, you'll suffer full or partial vision loss before sort of treatment is administered. And in India, 45% of patients lose vision or some full or partial vision before they're diagnosed. So it turns out now that computer vision works to detect Doberman shepherds, German shepherds and Dobermans and all kinds of other cars, it also works for assessing a retinal image into one of 5 categories. No diabetic retinopathy to severe. And it turns out you can just adapt the basic neural network architecture we're using for general image models and train it on retinal images. And if you do that, you get something that is basically on par or perhaps slightly better than ophthalmologists at diagnosing and assessing diabetic retinopathy. So this was a paper published at the end of 2016, which is pretty cool. But what you'd actually want is even better care. And so it turns out if you get the data labeled by retinal specialists who have much more training in diagnosing retinal diseases, and you use what's called an adjudicated protocol. So you essentially get 3 retinal specialists in a room, and you ask them, what do you collectively think about this, rather than getting 3 independent opinions. That turns out to allow you to get to a much higher level of accuracy. You want to be kind of all the way up in the upper left corner here. And so we're basically on par with retinal specialists now rather than general ophthalmologists. And that's kind of the gold standard of care. That's what you want everywhere. And one of the things that the community has been working hard on is how can we explain the decisions these kinds of algorithms and systems are making to the users of the system, in this case, to ophthalmologists. And so one thing an ophthalmologist might want to do is show me where. So given this, the model is output moderate diabetic retinopathy, level 3 output. But we can actually use this to show where in the image the system is focusing on in order to make that assessment. And that's a really helpful thing. In general, interpretability of these models is a really important thing as we sort of pair humans with machine learning systems in order to make better decisions. OK. The 14th of the categories was engineer the tools of scientific discovery, which I think was just like a grab baggy thing they threw in because lots of stuff would fit under there. It's a little less focused than the others. But it's clear that if machine learning is going to be at the core of a lot of the ways in which we do science, then we're going to want good tools for machine learning. And so one of the things we've been doing in our group is putting together software that enables us to do machine learning research and to try out things quickly, express machine learning ideas. And this is kind of the second generation of system that we've been putting together for deep learning research. And we decided we would open source this second generation system, which is called TensorFlow. And we open sourced it at the end of 2015. And it's had a pretty good adoption curve, which is good. This is showing GitHub stars. So when you have a GitHub as a place where lots of open source software is hosted, and people can star repositories they're interested in sort of following or getting updates on. And that's TensorFlow in the green line there compared to a bunch of other open source machine learning packages that were all created at different times. So we've had pretty good adoption, lots of metrics. 50 million downloads for like a fairly obscure machine learning kind of programming environment software is pretty interesting. One of the things I'm really excited about, and the reason we open sourced it, is the 1,900 contributors. About a third of those are people at Google, and the rest are people from lots of other big companies, lots of small companies, people, independent students, making contributions to improve this core set of systems that we're working with. That's cool. And people have done interesting things with it. So like there's a company in the Netherlands that is building fitness sensors for cows so that you can monitor your dairy herd and understand cow number 7 is not feeling so well today. And they use TensorFlow to analyze the sensor data. A team between Penn State University and the International Institute of Tropical Agriculture in Tanzania built a deep learning-based model using TensorFlow that can run on device in the middle of a cassava field to help you assess what disease your cassava plant has and how you should treat it. And this is a good example of where machine learning really wants to run in lots of places in the world, in large data centers, but also on a phone in the middle of a cassava field with no network connectivity. So it's really important that we build the right hardware and software tools that enable models to run on that and also much larger systems. OK, one of the things I'm excited about is how can we sort of automate the process of creating successful machine learning solutions for problems. And one of the things that our research group has been working on is a technique that's called AutoML, essentially learning to solve problems. And I'll describe a few pieces of research here and then sort of show how it works. So currently, when you want to solve a machine learning problem, you get someone with machine learning expertise, which is hard to find generally, and you have some data about a problem you want to solve. And then you have some computational resources, GPU card on your desktop, or maybe you're using the cloud, so you use a bunch of GPUs or TPUs or whatever. And then the machine learning expert kind of stirs this all together a few times and hopefully comes up with a solution. So what if we could turn this into more like data plus computation gives you a actually high-quality solution for problems you care about? That would be amazing, right? Because the problem today is that there are literally tens of millions of organizations that have machine learning problems in the world. Most of them don't even realize they have a machine learning problem, let alone have machine learning experts on staff. And there's only tens or maybe hundreds of thousands of people in the world who have the skills to sort of know what to do to train a machine learning model. That number is growing, by the way. If you look at enrollments in machine learning courses at every university, they're skyrocketing because sort of like the initial research paper graph. But it's still the case that it's going to take us a long time to get enough people trained to solve all the problems we should be solving. So what can we do? So one technique is called neural architecture search. So when you sit down as a machine learning expert to solve a problem with deep learning, you make a lot of decisions about what kind of model you're going to train. Is it like a 13-layer model? Is it going to use 3x3 convolutional filters at layer 7 or 5x5? What learning rate should it use? How should the layers be connected together? Is it just a linear thing, or are there skip connections? Lots of decisions like that. So what we're going to do is we're going to have a model generating model. And it's going to generate a model description. And then we're going to try that model on the problem we actually care about. And we're going to do this. We're going to generate 10 models, train them all, and then use the accuracy of those generated models to then steer the model generating model away from solutions that didn't work very well and towards solutions that work better. OK, so basically that. We're going to iterate a lot of times. We're going to generate models, train them, generate models, train them. And eventually, we're going to get higher and higher accuracy models. And that's great. They look a little weird sometimes. This is not what a human might sit down and design. But this turns out to be a highly accurate model for a particular problem. That's OK. And if you look at this, this graph shows you for image recognition, actually the ImageNet challenge problem. The black dots on the dotted line at the bottom are sort of each a really interesting model that was created by a team of machine learning and computer vision experts, best in the world, advanced the state of the art at the time it was published over the last, these were all sort of developed in the last 4 or 5 years at various times. And that's kind of the Pareto frontier of computational cost on the x-axis and accuracy on the y-axis. Generally, you get more accuracy if you spend more compute. And so in 2017, we used a set of techniques and got results looking like the blue dotted line there. And in 2019, we've been able to significantly improve on that. And the interesting thing is, this approach is better than all the machine learning experts hand designing different kinds of models. And this is true for object detection. So again, those bottom lines are various hand-engineered architectures. And the top line there is an AutoML approach, designing architectures. Same thing in language translation. And again, the metrics vary, but you want to generally be up and to the left. And same thing in tabular data. We're starting to get really good results on, let's say you just have some relational database and you want to predict one thing from all the other things. Turns out there's a site called Kaggle, which hosts a bunch of these kinds of competitions to see how well things do. The AutoML system that we've put together is in the blue there. And it's basically better than, for the 3 problems on the right, better than 95 to 98% of all the Kaggle competitors. One problem, it's sort of in the 45th percentile or something. And they recently had a contest for one day, given a completely new problem, 76 teams, 75 teams, I guess, plus our AutoML software. And the AutoML system placed second. It was in first until the last 4 minutes, and then Erkut and Mark entered one more solution. But it's pretty good. And it turns out you ensemble the Erkut and Mark solution and the Google AutoML solution, and it beats both of them. So that's cool. So this is across a lot of domains. We can now create systems that are working much better than the best human-crafted solutions. So the other thing that's interesting is we need more computational power. Obviously, if we're going to start training lots and lots of models for each problem we care about in an automated way, we would like computation of this form to be as cheap as possible. And the really interesting thing about these approaches is that deep learning really has different kind of computational style than traditional twisty C++ code you run on CPUs. And the 2 properties it has are that all the algorithms that I've shown you, all the machine learning models I've shown you, are all very tolerant of reduced precision. If you do computation to kind of 1 decimal digit of precision, that's fine. And also, all the things they do are different compositions of a handful of very specific operations. Essentially, linear algebra kinds of operations, matrix multiplies, vector dot products, and so on. So if you can design computers that are really, really good at reduced precision linear algebra and nothing else, that's perfectly fine. And you'll be able to specialize those computers so that they take advantage of just doing those things and not everything else. So we've been doing this for a while. The first generation of this system was designed for inference. Once you already have a trained model, how do you apply it and get predictions from it for different problems? If you have an image recognition model, feed in an image, and it gives you the predictions by running the model. And this is kind of the first thing that we deployed in our data centers. We started designing it in 2013 or so. It's been in production use since 2015, because designing chips takes a while. And it's used on every search query. It's used for all of our neural machine translation. It's used for speech recognition, image recognition. It was used in the AlphaGo match that our DeepMind colleagues played against Lee Sedol in Korea and Keji in China. And then we've been focused since then on designing chips for inference. So for inference and training. So the second generation and the third generation do both inference and training. And they're designed to be connected together into large configurations called pods. And so the latest generation TPU v3 pod is 1,024 of these chips. One of those is more than 100 petaflops of compute, which is pretty reasonable. It's reduced precision, so it's not directly comparable to top supercomputer sort of petaflops, but top supercomputer I think is like 150 petaflops or something. And this is one system. We have lots of these systems. And with this system, you can train an ImageNet model from scratch in 2 minutes, less than 2 minutes. Whereas that used to take several weeks. And you can imagine this just generally speeds up your ability to do research. If you can get an answer to a question you had in 2 minutes instead of 3 weeks, you just do a different kind of science. OK, so what do we want? I think we're training models in kind of a wrong way. Like we generally are training a model for a particular task from scratch. Or sometimes we're doing transfer learning or multitask learning of a handful of related things, but not every problem we want to solve. So I think we want a really large model that can do many, many things, but sparsely activated. So that maybe it's on 1,000 computers, but we only touch 50 of them to do one particular thing. And we touch a different 50 of them to do a different thing. And we want to solve literally hundreds of thousands or millions of tasks with this single model. And we want to dynamically learn pathways through this large model that make sense for different tasks, possibly sharing pieces of computation across different tasks when it makes sense, but having independent pieces where that makes sense as well. And the architecture should adapt, kind of like with neural architecture search. Adding new tasks will leverage skill and representation. So a cartoon diagram to conclude. Let's say we have this system that can already do a lot of different things, and we add a new thing. Oh, and it's made up of components which are some piece of a machine learning model with state and operations. In a neural network, operations might be forward and backward. So let's add a new task. And now let's imagine running some sort of pathway like reinforcement learning search to find something that gets us into a good state for this new task. So great. So now we have something that has leveraged some of the representation it's learned for other tasks. Now let's say we want to improve that task. Let's add a component and extend the model a bit for this task. And now we have, hopefully, a higher accuracy system. And that new component can now also be used across other tasks. And each component might be running some sort of little architecture search to adapt to the kind of data that's being sent to it. OK, I'm going to close with thoughtful use of AI in society. I think if you look at the breadth of things that these systems are touching, it's really important to think about how we want machine learning and AI to be applied. And one of the things that I'm proud of is that we, as a company, have put together a set of principles, and we've published them in public, about how we think about thinking about new applications of machine learning. Should we use machine learning for this problem or that problem? And there's a lot of real issues here. Like in particular, the second one, avoid creating or reinforcing unfair bias. If you think about what machine learning systems do, they learn from data. And if you're learning from the world as it is, rather than the world as you'd like it to be, you can perpetuate biases or even accelerate them by being able to do things in a more automated way. So just to give a sense, what we're trying to do is apply the best principles we know how to, but also advance the state of the art in, for example, how do we eliminate bias from these models? And just to give you an example, we've been publishing lots of papers on sort of fairness and bias in machine learning. So this is an active area of research We want to use whatever the best known techniques are, but also push those beyond. So with that, I hope I've partially convinced you that deep neural nets are doing really interesting things across a broad range of fields. And they're going to affect not just computer science, but like nearly every discipline. Think about the fact that computers can see. That has enormous ramifications in and of itself across many disciplines. So thank you. If we have time. One question. Great. I will come back up. Here I am.
Can I do the question? Hi, very nice talk. So one question is you hinted to maybe the energy consumption.
Yeah.
So for the current self-driving cars, how much energy we spend on top of the usual cars we drive a day?
So the energy consumption of autonomous vehicles is actually not all that different from a traditional vehicle. It really largely depends on the drivetrain mechanism that is used, and it's not that different whether it's autonomous or not. I think there will be energy efficiencies from the fact that it is autonomous, and if you were imagining controlling a large fleet of these, you can imagine routing things more efficiently so that you need fewer cars on the road, perhaps, and that cars appear in the right place at the right time with the right size car. But that's sort of a farther off kind of thing once we have a lot of these actually on the road. Does that make sense?
Yeah. And the deep learning, how do you prevent adversarial attacks in your paradigm?
Yeah, that's another area of important research, like safety and adversarial attacks on these. I didn't talk about it in this talk, but there's a long thread of research in adversarial techniques to prevent sort of images that look like a stop sign from being interpreted as a 45-mile-an-hour speed limit sign. Say. Thank you.
Hi, it's my pleasure to introduce Daphne Koller. She is the CEO and founder of InCitro, which is a machine learning-based startup working in drug development. She's also the co-founder of Coursera, which is a massive open online course system, which I think many of us have heard of. She was the Rajiv Motwani Professor of Computer Science at Stanford, and she's now adjunct there. And she was also the Chief Computing Officer at Calico, which is an Alphabet company working in healthcare. So those are sort of the posts she's held. But she also has a lot of other feathers in her cap that I'd like to mention. And I only have 2 minutes, so I can't go through all of them. I did try to scrub the bio that she provided, and also her Wikipedia page, which in itself is a feather in her cap that she has a Wikipedia page. But some more notable honors she's received is that she was a MacArthur Foundation Fellow. She won the ACM Prize in Computing. She's a member of the National Academy of Engineering and a fellow of the American Academy of Arts and Sciences. And if you hadn't heard of her from all of these things, you may have seen her in the media because she was named one of Time Magazine's 100 most influential people in 2012 and one of Newsweek's 10 most important people in 2010. So I'm, needless to say, really look forward to hearing what she has to say. Thanks.
Thank you, and thank you for inviting me here. So for most of my career, with the exception of the detour through Coursera, I've been working at the boundary of 2 disciplines, machine learning and the life sciences. And I use the word boundary rather than intersection judiciously, because much as I would have wished it to be otherwise, there hasn't really been that much of an intersection between those 2 disciplines until recently. And what I hope to convince you today is that that is changing, and that that's actually going to be a new era in science that I'm personally very excited to be part of. So I'm going to start with the problem that we're setting out to solve in this next chapter of my life, which is the problem of therapeutics, or discovering new drugs that make people better. And there's an area where it's both good news and bad news. The good news is that when you look at the history of
therapeutics in the last 50 or so years, there's been a tremendous amount of progress with new waves of innovation that have been making a difference in treating new categories of disease. So starting from vaccines as one example, biologic therapeutics, which came about in the 90s, that have allowed us to address certain types of cancer effectively, certain kinds of autoimmune diseases effectively. So of the current 10 top-selling drugs, 8 are actually biologic therapeutics, which is quite remarkable. Cancer immunotherapies, of course, have now gotten to the point where some people with metastatic disease, not as many as we would like, but still are now able to have a complete cure from their disease, which is unheard of as of a few years ago. Targeted therapies for genetically driven diseases is one of my favorites because it's one of the first real advances that have been driven by the Human Genome Project. So cystic fibrosis is a great example of that, where by understanding specific genetic lesions that occur in the gene CFTR and targeting drugs specifically to those lesions, we're now able to give an effectively normal life to about 90% of cystic fibrosis patients, whereas a few years ago this would have been a death sentence. And then, of course, new generation of therapeutic modalities that are emerging, gene therapies, cell therapies, and many more. So that's great, and that's the good news. The bad news is this interesting graph, which for those of us who grew riding the tidal wave of Moore's law, it's a kind of ironic graph. It's come to be called Eroom's law, which, as you notice, is the inverse of Moore, because this is a graph on an exponential scale where the x-axis is the number of drugs approved per $1 billion of US R&D spending, and the x-axis is time. And you can see that consistently for over 50 years, there has been fewer and fewer drugs approved per dollar amount over time. And that doesn't seem to be shifting despite all of this amazing progress that I've shown on the previous slide. So why is that? It is not the case that a drug that used to cost $100 million to develop start to finish now costs $2.5 billion, which is, by the way, actually the amount now quoted is closer to 3. So what is going on here? What's going on is that we have a lot more stuff that we try in early stages of the drug development pipeline that over time falls by the wayside because of failures that happen at different stages. And each of those stages is really expensive and complicated. Drug development is really hard. And so by the time you get to the final regulatory approval of a single compound, it carries on its back the costs of tens of thousands of failures that have cost many millions of dollars. So when you think about what that really means is that this is ultimately a problem of prediction. If we could predict earlier on which scientific hypotheses are likely to work, which drugs are likely to succeed, we would be able to eliminate a good portion of those failures so that each successful drug might carry less weight on its back and be cheaper to develop. Now, machine learning has gotten really good at making predictions. We heard about that from Jeff. So the question is, can we use machine learning to address multiple prediction problems that come up in the drug development process so that we're able to try fewer things that fail and have a higher success rate? And so that's really the problem that we're looking to solve. Now, there's many different problems that one can focus on in this space. I'm going to focus on the one that we're starting out with, but there are others that one can tackle over time. But the fundamental problem in drug design is, if I make this intervention, this therapeutic intervention in a person, what is it likely to do? What phenotypic effect is it likely to have? So that's the problem that we set out to solve. And you ask yourself, well, obviously, this is being solved in drug design today, so what do people typically do? What they typically do is use model systems, mouse being the one that's most ubiquitously used. And so you put a drug in a mouse, you see what it does to the mouse, and say, oh good, this is what I infer from that what it's likely to do to a person. The fundamental problem with that, and I know this is going to come as a shock to you, is that mice are not people. And furthermore, most of the diseases that today serve as an significant unmet need are ones that mice do not get. And so people have gotten really creative in using mice to build model systems for disease in ways that are, let's say, creative but might not be effective. So I'll give you one of my favorite examples. I could talk for a lot longer on this. The mouse model for depression is called the forced swim test. You take the mouse, you put it in a pool. You let it swim until it drowns. If it swims longer, it's less depressed. Okay? Now, then you wonder why there have been so few psychiatric drugs approved over the last few years. By the way, the ones for neurodegeneration are not much better, but we can talk about that later. So the fundamental thing that we would like to do is to use humans as a model for humans rather than mice. Now, of course, you don't get to experiment in humans. That's not ethical, it's not practical. But fortunately, there are other data sources that we can bring to bear in order to produce the kind of training data that we need to drive machine learning models. So one of those is human genetics. Each of us is actually an experiment of nature in which nature has perturbed the genetics of a particular person, and we can see the effect on phenotype and what it does to disease. And sure enough, there has been evidence, quite a bit, that has shown that drugs that have genetic validation, that is, where we see a phenotypic effect in a human using genetic data that is commensurate with what we would like to see from the drug that targets that gene, those drugs tend to be more successful. So this is one way of showing that. There's others. This is the percent of drugs in the pipeline at different stages, ranging from preclinical all the way to approved, that have genetic validation. And what you see that as you move further in the pipeline, the ones that have genetic validation are less likely to attrit. So you have a higher percentage of drugs with genetic validation among the approved drugs than you do at the earlier stages, suggesting that those are ones that are likely to be more successful. So that's great. And sure enough, we now have more and more genetic data that is available to us on people. So this is actually a Moore's law, not an Eroom's law graph. So the x-axis, again, is an exponential scale. The y-axis exponential scale. X-axis is time. This is the number of human genome sequenced since the very first human genome in 2001. And you can see that that graph is not only growing exponentially, it's growing exponentially twice as fast as Moore's law. So if you believe that this historical trend will continue, then by 2025, we will have approximately 2 billion human genome sequenced, and that's a lot of data. So that's great, but genotypes on their own are not enough. You need genotypes associated with phenotypes or traits. And this is a place where progress is also growing. It's not quite as fast, but there are resources like this. This is one of my favorites. It's the UK Biobank dataset in the UK. And it measures for 500,000 people very detailed phenotypes along with the genotypes. So things like biomarkers, both blood and urinary, behavioral data, physical traits and so on, as well as imaging of whole body, brains, and so on and so forth. And now you can really start to look at these data and associate them with genotypes. By the way, this is one of the best of the resources, but there's other ones that are emerging, including one here in the US called All of Us, which is just kicking off. So this is great. And now you can say, okay, we have genetics, we have phenotypes, so we can now do an association. This is usually done using a fairly simple statistical methodologies like linear regression. And you can now do these associations. And over the past 10 years or so since this first kicked off in around 2008, there has been a growing number of genetic associations that have been uncovered, ranging from things that are molecular in nature, like LDL cholesterol, to things that are diseases, like Crohn's disease or Alzheimer's, even to things that are not even diseases, like educational attainment turns out to have a pretty strong genetic basis. So this is great. And you think, well, okay, we're done. We have the genotype to phenotype mapping. The problem is that this is kind of challenging, because when you think about the genes that are mapped to phenotypes, we don't really know what they mean, and they're often quite small in their effect. So the typical effect size, so first of all, look at these, and you can see that for many of these diseases, there's hundreds of variants, 100, 200 variants that have been, or loci, genetic loci, that have been associated. Each of those has multiple genes in that region. And when you start looking at the actual genetic changes, very few of them are ones that scream out at you, I know what this means. It's in a coding region, it's a loss of function. A lot of these are regions of the genome that are the dark matter, where we don't even know what that means. And so, and the effect size that they have on the phenotype is often quite small. You know, an odds ratio of 1.03 is typical. So how do you interpret those and use them as a way of discovering drugs. And sure enough, it turns out to be a challenge. So if you look at this example of this graph again, where you think about what is the extent to which you get benefit from having genetic substantiation for a drug, and this is a different way of visualizing the graph that I showed before, you can see that overall you're twice as likely, if you look at the bottom, at the rightmost graph, you're twice as likely to go from preclinical to approval if you have some genetic support. But really, the biggest gains are obtained for what's called Mendelian traits, which are in the OMIM data set, which are very high penetrance, coding level changes, where we know exactly what they mean. When you start looking at the support from genome-wide associations, that benefit is considerably lower. So the question that we need to ask ourselves is, can we leverage genetics much better? So one question that you might ask yourself is, well, maybe all those other variants genuinely don't matter and there's nothing to leverage. So a beautiful paper from Sekatherison's group at Harvard that came out at the end of last year shows that that doesn't seem to be the case. So he defined what's called a polygenic risk score. I mean, he didn't define it, it was there before, but in this paper, he constructed a polygenic risk score that doesn't just look even at the top 200 or so variants, looks at 2 million variants across the genome, and puts them all together in a linear score called a polygenic risk score that gives you this beautiful Gaussian distribution of risk. And it turns out that as you move to the right-hand tail of this distribution to people who are at greater risk, you can see that there is 8% of the population, this is for cardiovascular disease, that has a 3-fold risk of disease. If you have enough small variants that contribute negatively to your genetics, then you have a 3-fold risk of disease, 4-fold, 5-fold, and as you move to the right, it can be even as much as 8 or 10-fold. So there is a lot of signal, and by the way, 8 or 10-fold is as much as you get from a Mendelian high penetrance variants. So there is signal in this distribution, it's just that we don't know how to interpret it. So how do we plan to go about that? Well, fortunately, biologists have provided us with yet another valuable tool, which is the ability to generate very large amounts of biological data that are disease relevant. And I'm going to talk about that next. So a case study, just to illustrate what we mean by this. This is an image of a stained cell culture of neurons. And the green are nuclei. The blue are nuclei, the green are synapses, and this is what it looks like. And now we're going to look at this in the context of a particular genetic variant that we do not understand. This is a region in chromosome 16 called 16p11.2. And for whatever reason, that region tends to have a lot of genetic changes in the population. There's people in whom it's deleted. There's people in whom it's duplicated. So if this is what the wild type, and it turns out, that in the deletion, the autism penetrance is 75%. That is, for people in whom it's deleted, 75% of them have autism. In the people in whom it's duplicated, 40% have schizophrenia. There's around 25 genes in that region, and we have no idea which of them causes these phenotypes. If it's the same gene for both, if it's more than one gene, none of that is known. Only those numbers are known. So in this 2017 paper, people started to use a really wonderful tool for getting at the biology of this, which is to take cells, epithelial cells, skin cells, from people who have wild type or one or the other of these variants, reprogram them into stem cell, which you can now do because of the great work of Yamanaka, for which he got the Nobel Prize, and then differentiate them into neurons. So we can do that for any single one of you. We can take skin cells, reprogram them into stem cells, and generate neurons or cardiomyocytes or hepatocytes or whatever. Well, it turns out that if you do that for people with a deletion, you get an incredible excess of synaptic arborization. And for people with the duplication, you get a significant depletion of that synaptic arborization. And you can see that by eye, and you can also quantify that to a certain extent by looking at these images. And you can see that the soma area changes, the dendrite length changes. So this is great. And it gives you the first inkling for the mechanistic process that generated the disease. Now, the thing is that to do this work takes 3 years, and it was done in about 3 patients of each type. So it's an incredible amount of work to do this. But what if we do this differently? So biologists have now, in the last few years, created these remarkable tools. The first one is the one that I just told you, which is the ability to create cellular models that are disease relevant. Up until 5 years ago, most biological experiments were done in cancer cells. Now, not only are these cancer cells, so they're not really normal, they've been passaged so many times that by the time you get to look at them, they have 8 copies of one chromosome, 0 copies of another, because these cells are genetically unstable. Today, we can do this for cells that really resemble normal human biology. We can perturb them genetically using CRISPR to do very fine-grained changes that might mimic the genetics of disease so that we can now start interpreting those variants. And we can phenotype those cells using imaging, just like the ones I showed you before, to really give us an inkling of what's going on at the cellular level for patients that have different variants of the disease. And importantly, putting in another piece of progress, because of high-throughput automation and microfluidics, we no longer have to spend 3 postdocs pipetting for 3 years in order to get data like the ones that we saw. We can really generate incredible amounts of data at scale to allow us to have this level of understanding. And so you can really build, at this point, a data factory, if you will, that allows you to generate this kind of data in a remarkably scalable way. So that, of course, gives us way more data than people can interpret. And that's where machine learning comes in, is to interpret data that look like this. So that brings me to machine learning, and I'm going to actually skip past these slides because Jeff did such a great job of laying the ground for me about how much progress machine learning has made since 2005, where we could barely tell what was in this image, to 2012, where we kind of were guessing sort of okay, to 2017, where we're able to caption these at beyond human level performance. And this is, again, thanks to Jeff. I don't need to take you through the fact that the key benefit here is that people no longer need to construct features that tell the machine what's important to look for in these images or not. You just give them the raw pixels as data. Now, that was important when you're looking at cats and dogs and bears. It's even more important when you're looking at synapses and neurons, because whereas people are really good at looking at cats and dogs and bears, they're really not so good at looking at images of neurons and synapses. And so their ability to construct meaningful features in that domain is considerably lower than in the case of natural images, where even their machines outperform humans. So certainly when you start to look at synapses, you would imagine that machines will considerably outperform humans. So one thing that Jeff didn't touch on and is important to what we're doing is the understanding that that potentially gives us about the space, the underlying space of, that we're looking at. So when you construct these neural network models and you look at the next to last layer of the neural network, it gives you an embedding of what is a very high dimensional space into a much lower dimensional space. So if you think for just as an illustration about the space of all images, let's say for simplicity, 1,000 by 1,000, let's say for simplicity, it's grayscale, these images live in a 1,000,000 dimensional space. Most of that space is filled with white noise images that don't mean anything. The space of real natural images sit in a much lower dimensional manifold within that space. By training the neural network to a particular objective, you tell it how these images in that low dimensional manifold relate to each other and how images that you would like to be labeled similarly need to be next to each other in that space. So when you're labeling, when you're forcing the network to label images with natural categories, you're going to be forced to put these 2 images of trucks that visually are very distinct in terms of color and pose and texture. You're forcing the network to learn that they need to be next to each other. Whereas things that are somewhat related but not quite the same, like tractors and cars, are going to be relatively adjacent, and cats and dogs are going to be sitting somewhere else in that manifold. That manifold gives you if you look at it, a deep understanding of the disease, of the space, and therefore can tell you something about the space that you're looking at. And I'll come back to that in a minute. Okay, so now we're going to take machine learning and we're going to see how you might apply this back in the domain that we talked about. And so machine learning applied to images of cells is not a new thing. In fact, one of the papers that I'm actually still the proudest of that I did just before I left Stanford in 2011 was the application of machine learning to digital pathology. This was back in 2011, pre the deep learning revolution, so we were using traditional machine learning. But fortunately, I had a pathologist as a PhD student who was able to construct meaningful features and was also open-minded and said, we're going to construct many, many, many features that pathologists have never, ever looked at. And that turned out to be highly significant. So when we looked at these tumor images under the microscope with these hundreds of features that pathologists had never looked at, we were able, via machine learning, simple machine learning, to get performance that was better than the average pathologist. So what you see here is what's called the Kaplan-Meier survival curve. X-axis is time. Y-axis is patients who are still surviving at that point in time. That is a curve that unfortunately goes down and to the right. And what you see is the stratification between high-risk patients at the bottom and low-risk patients at the top that the machine learning was able to come up with. And you see a pretty good stratification that was, at the time, better than your average pathologist. What was equally important, though, is that the features that the machine learning was using were exactly the ones that pathologists had never, ever looked at, demonstrating that looking under the lamppost is usually not the right strategy. So fast forwarding now to 2018, now you have machine learning algorithms that are doing this type of problem not only better than the average pathologist, but better than the best pathologist. And you can see on the left is the Kaplan-Meier curve for the pathologist, and on the right, the Kaplan-Meier curve for the machine learning, better stratification. And what I thought was actually even more interesting is the ability to do something that pathologists just don't do at all, which is by looking at these images, tell not only what the prognosis was, but also what is the driver genetic mutation that gave rise to the tumor, which has huge clinical significance. So I think this is a demonstration that when you look at these images, machine learning is able to do things that a person cannot. That's, again, the good news. The bad news that I'd just like to highlight, because I think it's a good warning lesson to all of us, is that machine learning is, when applied to biology, something that one has to be really careful about. And I think that's true in general, but it's even more true in biology. And I'm going to use this as an example because it was a published piece of work that focused exactly on this. There are plenty of people who don't realize that their machine learning is doing this and don't bother to check well. But this is, this is a paper that looks at identifying fractures from X-ray images like the one on the left. And what you see in the graph on the right is the ROC curve. And you say, look at this. Oh, this is doing pretty well. You know, it could be better, but it's doing pretty well. Well, these folks were smart enough to actually look at what the network was learning. And these are the clusters that you get in the low-dimensional manifold, visualized via t-SNE at the, and you can see that the fracture versus non-fracture are actually kind of intermixed in the clusters that you learn. What's not nearly as intermixed is the scanner that took the scan. So it beautifully stratified on the cluster, on the scanner that took the scan. And it turns out that when you correct for that, the performance becomes effectively random. So what the machine learning was learning is which scanner took the scan and using that to infer whether the patient had fracture or not. Now, we can speculate why it is that certain scanners are used more predominantly for fracture cases versus not. That's besides the point. The point is, deep learning is really good at homing in on subtle signal. It's also really good at homing in on subtle artifact. And artifacts are really rife in biological data because biological systems are very sensitive. And so you can really create artifactual results that have zero biological value. And that's one of the things where industrialized biology really can make a difference. So coming down to what it is that we're actually doing to put this all together, we're building what we think of as the in situ human platform. We can take data from patients and controls. There's not going to be a lot of these. If you're lucky, you get cells from a few hundred patients, maybe 1,000 patients. That's about as many as you can get. You put them in what is a 100,000 dimensional space that you can look at when you think about the images or single-cell RNA-seq or metabolomics or whatever. 100,000 is actually on the low ball from the estimate. You don't really see anything because these are a very sparse number of points in a very high dimensional space. But now is where you can use some of the tools from genetic engineering that we've talked about to considerably expand the space of genetic backgrounds that you look at, so that now all of a sudden you don't just have the patients and controls in your space, you also have lots and lots of other types of genetic backgrounds that you can now measure and look at the cellular phenotypes for. Now all of a sudden structure, like that low-dimensional manifold, emerges using the right application of machine learning tools. And what you can now do with that is to look at this diagram and notice now, whereas you couldn't before, there's distinct clusters in this space that correspond, hopefully, to coherent patient populations. And each of those patient populations might benefit from a different therapeutic intervention that will allow you to revert the phenotype from sick to healthy. So by doing this, you're now also able to move away from the current paradigm of doing medicine, which is to take an entire ensemble of patients who characterize their disease by very coarse-grained phenotypic summaries, and say all of these should benefit from the exact same medicine. We know that's not the case. The thing that's made oncology so successful in the last few years is the fact that we now understand that breast cancer is not one thing, and that there are certain types of breast cancer that are actually much more similar to ovarian cancer or pancreatic cancer than they are to other subtypes of breast cancer. And by giving a HER2-positive breast cancer patient a very different treatment than you give someone who has a BRCA mutation, then you actually end up getting the kinds of success rates that we've been getting in oncology, is by understanding that there is so much variability and heterogeneity in the patient population. The CFTR example, the cystic fibrosis one that I gave you earlier, by sequencing the CFTR gene, we know exactly what is the genetic variant that caused the disease. And each of those, there's 3 subpopulations, each of those has a different drug. That's what made this success possible. So if we're able to do that for the diseases that we don't currently have this characterization form, like autism, which is called spectrum for a reason, then maybe we're able to now understand those subpopulations and construct the appropriate intervention for each one of those. So in order to do this, we need the right combination of biological data factory and machine learning. We need to construct biological data at an unprecedented scale. We need to be able to interpret that data using machine learning. We need to feed back that insight from the machine learning directly back to the biodata factory in a very tight, closed-loop integration. Yes. I'm almost done. And in order to do that, we also need to have the right group of people. We need to have people who are bilingual and really able to talk the languages of both biology and machine learning at the same time. So I'm going to end, with a philosophical note that brings us back to the beginning. If you think back about scientific progress, you can see that in certain times of history, science has proceeded in epochs where in a certain short period, that a particular discipline has made an incredible amount of progress in a short amount of time due to a new insight or a new technology. In the late 1800s, that discipline was chemistry, where we moved away from alchemy and turning lead into gold into an understanding of the periodic table. In the 1900s, in the early 1900s, that science was physics, where we split the atom, understood the nature of the connection between matter and energy and between space and time. In the 1950s, it was digital computing, where you got a device to duplicate computations that up until that point only a person had been able to do. In the 1990s, there was a really interesting split. On the one strand, there was data that emerged directly from computing, but I think it's a discipline that stands on its own because it also incorporates elements of statistics and others. On the other strand, there was biology, or quantified biology, which rests in all of those developments in chemistry and physics and has given us the sequencing of the human genome and the ability to measure transcriptional profiles and the ability to look at cells with super resolution microscopy so that you can actually pinpoint individual molecules within the cell. And these two strands basically proceeded in parallel with very little interaction between them. I think the next epoch of science, and in this I'm actually echoing in some ways Steve Jobs, who made this prediction multiple years ago, that the next big epoch of science in this century is going to be the integration of biology and technology. And you can call this biological data science or biological engineering, or I don't know what it's going to end up being called, but it's the ability to measure biology at an unprecedented scale, to interpret what we see using machine learning techniques, and to feed those insights back to engineer biological systems to do something that they don't normally want to do. And I think that discipline is going to transform the 21st century. Thank you very much.
So I have, well, thanks for the talk, very interesting one. I'd like to make you two questions. I think the first one is easier than the second one. So I'll start by the first one. When you compare the performance of the machine learning algorithms for detection of different diseases versus the specialists, I cannot see never in the comparison how many resources are being used from the algorithm to develop these predictions versus the prediction that is done by the specialist, by the human.
Sorry, I'm having a really hard time. Maybe you can speak closer to the microphone. I'm sorry.
Now it's better?
Yes, thank you.
So
Oh, no, but I think this is, yeah.
Okay, the first question is about how to compare the predictions made by the algorithm, in your case, versus the predictions made by the specialist, not only on the actual performance of prediction, but on the efficiency of creating that prediction. So, for instance,
The question is about
Yeah, I get it.
computing resources are needed to do
Yeah. So I think there's two questions. One is on the computing resources and one is on the accuracy. So this is very hard to do apples to apples because we're not doing diagnosis here. We're doing drug development. And so the ultimate product, if you will, is a drug. And so the question is, fundamentally, does the drug work better than the standard of care? That's something that we will only be able to tell when we actually have a drug and put it in humans and it undergoes the standard process of randomized clinical trials, as one should. So the comparison, this sort of, neck-to-neck comparison, if you will, between predictions made by a human and predictions made by a computer, which makes a ton of sense in the context of diagnosis, don't really make that much sense in the context of drug design. As to the compute power that's used, we don't know yet. It partly depends on how well Jeff and his team are going to be doing in creating new versions of TPUs and new machine learning algorithms that we could leverage. But when you think about the fact that drug design from beginning to end is approximately a 10-year process if you're lucky, then if it takes you a month to do the computing versus 2 months to do the computing, honestly, it doesn't matter very much. Even the costs don't matter relative to the $2.5 billion worth of cost that it's currently costing us to do drug development, which is one of the reasons why I think this is so important, because any improvement, even if 10% is going to be, which I hope we can do better than that, is going to be hugely impactful.
okay, and that.
Thank you very much.
for the last session. Have a seat. No, have a seat. Have a seat. You're going to introduce yourselves. Mike. Oh my God, those lights! Jesus Christ.
It's like being on stage.
It's these Klieg lights. You can't see anything.
Actually, I need, I need to keep track of time because we have to be.
Oh, we don't have 40
not
minutes.
that. I'll do it here. It's okay. It's fine. Good afternoon. Welcome to the final session. So for the last session, it's a smaller panel, which I'm happy to moderate. Jeanette and Mike will introduce themselves in a second. We thought it was appropriate to conclude the day with a session that was more forward-looking. So it's about the future of data science. We have a hard stop here. We have to exit this room before 3 o'clock. So
That's why we've been rushing you all day.
yes. So without further ado, I'll ask the two panelists to introduce themselves, and then we'll off we go. So Jeanette.
I'm Jeanette Wing. I'm the director of the Data Science Institute at Columbia University and a professor of computer science.
Mike Jordan. I'm from across the bay, Berkeley, Computer Science and Statistics.
Great. So this is going to be quite unstructured. I'm hoping that our distinguished panelists will talk about many things, but I'm particularly interested in hearing their views on how data science, Research One universities should structure themselves in the era of big data and data science. That's one question, and another is about the relationship between data science and AI. So I don't know, who wants to start?
So I'd like to take the first question. In March of last year, I ran a summit which collected 65 participants from about 30 different universities. All of these participants were leaders in some way of some data science entity on campus. And just to acknowledge the funding sources were NSF, the Moore Foundation, and the Sloan Foundation. It was a wonderful meeting there because the bottom line was it's all over the map. And many universities are still struggling, or I should say grappling with, where do we put this data science thing? So there were a few models that emerged, and there's no one right answer. One is where, for instance, at Columbia University, the Data Science Institute is actually university level and university wide. It doesn't belong to any one school or any one department. It is its own thing. Another model is, for instance, at Yale University and I believe at Carnegie Mellon was, if you will, a renaming of the statistics department. So now it's statistics and data science. Take it as you wish. By the way, at Carnegie Mellon, there already had been and is still a machine learning department. So what's with that?
Another one for 40 years.
Another model is the Berkeley model. Oh, we'll create a thing called a division, I believe it is.
Let's call it college for this audience.
Well, no, I was told not to actually use, I'll use the word division because that's officially the word. And of now it's data and information science or something like that.
It'll conclude computing at some point.
At MIT, for instance, before the new College of Computing, before the huge gift, there was an Institute for Data Systems and Society, and I remember going to the inauguration of IDSS a couple years ago, and I asked Munter, who was leading it, I said, who do you actually report to? And he says, I report to 5 deans. So there's yet another model. And then there are, of course, more traditional models where the data science entity will live within a school or a college on campus. So literally, it's all over the map. Many schools are starting to think about creating a School of Data Science or School of Data Science and Computing. So it's really, it's a challenge for any university administration at this point.
And the right way is?
I like the Columbia way, but I'm going to say that, of course.
Mike?
So I think of this more as what's happening in the real world and less about academia. I think that's where the first thrust really was in industry. And I think that it's misnamed. I don't think this is about science so much. I mean, we had big data sets in science, but it's just that's statistics. What's new, I think, is something more akin to engineering. And that term of engineering, I think we have too narrow. You know, we think of cold, effectless machinery and loss of control by humans. But this is a new kind of engineering that is about building systems that really work in the real world for real people and reflect people's desires and preferences and so on. That's what it's about. It's about a human-oriented, data-oriented engineering field. So I kind of take the historical reference as maybe think about chemical engineering. So think about, you know, I didn't do the history yet, I'm going to do it, but think about the 20s or 30s. There were ingredients, there was chemistry, there was fluid flow, there was this and that lying around that people were trying to put it together. They didn't do a particularly great job at building factories at scale in the very beginning, but eventually they figured out how to do it. And new principles were needed, and eventually a name got given to that thing. It was called chemical engineering. And now there's a department of that everywhere. And that took a few decades. I don't want to give a name to this too soon, but I think it's more about engineering. It's about the Ubers of the world, the Amazons and the services and the markets that are being created about that. It's about market principles on top of flows of data. It's about the uncertainty in the real world that comes out. And so I think that academics, we kind of have to absorb those millennial changes and eventually create an academic discipline and structure and all that. But that's putting the cart before the horse to think about let's define this thing and let's think about the academic version of it. No, let's reflect what are the real world consequences of thinking about an engineering field that is affecting 500 million people daily and is flows of commerce, medicine, finance, you name it, and make those systems actually work and not work just for today, but work over time spans and not create messes around them. So I think, I hope from what you see from my latter comments, we're not there yet.
But may I?
Please.
Okay, so David said we can riff. So let me challenge you, Mike. So the purpose of today's meeting was to convene, two purposes, to convene the computer science and the statistics community to come together and talk about data science. But the other purpose was to really focus on what we've been calling foundations of data science. Whether you call it science or engineering, I think that's not the point. So do you see that by bringing together various disciplines, and I also want to include signal processing from EE and optimization from OR and so on, do you see that it does make sense to talk about foundations of data science?
Again, I think you're going back to academics, and I'm trying to pull us out of academics, because I don't think that's where the real phenomenon is happening.
Okay.
If you try to have a service in the real world, think about a recommendation system. So, I've spent some time thinking about that. A recommendation system will recommend books or movies to people. It does it at scale, it handles the long tail, it's economically viable, it's not just a piece of AI software that people hopefully use, it's a financially solid thing. But it's mostly been done in the computer for virtual objects like movies, that you can copy the bits and all. Think about doing recommendations broadly in all kinds of real-world situations, recommending streets to people to go down, recommending restaurants for people to be in, recommending financial services that people will avail themselves of, what stock to buy, what medical thing to use, and so on and so forth. You can start to see there's going to be conflicts, there's going to be scarcity, there's going to be game theoretic issues, and if you don't face those on day one and think of an engineering field that includes all those issues, you're not building a system that's really going to work. Right? And we see that, where people are building lots of systems that kind of work for a little while, and then there's all these problems that come up because they didn't think through all of the incentives, all the consequences, all the externalities around those systems. Yes, to build those kind of systems, you have to think about what academic past is needed, what some of the foundations might be, but it's kind of obvious. It's statistical inference, it's prediction, it's scalability, it's economic principles, microeconomics, game theory, and so on. But look at the problems you're trying to solve, and less about the historical fields that gotten certain names associated with it.
But be that as it may, there's a risk that it'll work out badly if we don't go about it in a planned fashion. And what's particularly in my mind as a statistician is in any major university there are statisticians all over the place. they call themselves psychometricians or biometricians or econometricians or statisticians or biostatisticians, and it's a problem because they don't talk to each other. So there's a real, we're missing an opportunity to have cross-fertilization.
Again, you guys are going back to academics, and that academics don't talk to each other is for 3,000 years. I mean, that, but no, I mean, at Berkeley we have a model where we talk to each other. I don't know what's happening at other universities. But we talk to each other across all those disciplines, and sometimes the same ideas get reinvented and all, but especially our grad students, they talk to each other. It's just gone. I mean, I think these academic issues are secondary. So yes, we have to figure out how to teach the undergrads, and that's one thing we focus on at Berkeley. Yep. The grad students will figure it out. I got no worry about them. But how to teach undergrads, that's an issue we could talk about. But yeah, no, the issues are the real world ones. The academics are secondary.
Should we have a PhD in data science?
No.
We will.
In 20 years, just like chemical engineering eventually had a PhD. I doubt they had one on day one.
But we will. Like within the next 3 years, there will be. Sure.
We might have
well,
one, but just
NYU
like
already has one.
But just like we had machine learning at Carnegie Mellon, and no one else copied. That 30 years later, it wasn't a great idea.
It was, or was not?
It was not a great idea.
Okay. What about this new division that Berkeley's created?
So data science temporarily, until it eventually evolves into its big form, is an umbrella term. It's the first umbrella term I've seen in my 25, 30 years. So think about someone who does databases, right? They work with data, right? So you ask them, are you a data scientist? They're mostly going to say yes. Yes, absolutely. If you asked them before, are you a machine learning person? They would have said no. If you asked if you're a statistician, they would have said no. Well, statisticians work with data. Aren't you a data person? No, I'm a different kind of data person. But data science, every statistician thinks they're a data scientist, and they rightly so. And a lot of other people do too, but including the database and distributed systems people. So that's why it was a useful umbrella term in the academic side, was because it allowed all those people to feel like they did belong together and they would start talking together. But that had already happened in industry. You can't go into Amazon 20 years ago or Google and the database people are completely separate from the statistics people. That just didn't happen. They had to solve a problem together. Yeah, so no, I think that it's so just like engineering or chemical field in the past, it's not a department-sized thing. It's not an institute. That's too small for it. It's an umbrella term, so it should be one of the new engineering disciplines emerging. So think about the colleges we have now in universities: biology, humanities, arts and science, physical sciences, and all. They existed 100 years ago. What new college do we have in the last 100 years? Basically nothing, right? And people wanted for a while College of Computing. That's too narrow. You need inference, minimally, and ideally economic and social principles. So now we're starting to perceive that. That's the college. That's why it should be a college. And just to say, at Berkeley, it takes 6 years to create a college because the regents have to rule in. So we couldn't call it a college yet. So we have to call it a division because you can do that today. But it will be a college because that's the right level of granularity of the whole enterprise. And I don't think it should be called data science because I don't think in 10 years it will be data science. It'll be some other new nice terminology will arise.
So what about AI? Let's switch topics. AI. What is AI and where does it fit in all of this?
So let me jump in first this time. So I wrote a blog post last year. Xiaoli Meng is in the audience, and he's putting in his first issue of Harvard Data Science Review. If you haven't already advertised that to this crowd, you did. All right.
He did.
He shamelessly
several
plugged it
times,
this morning.
probably. Yeah. So it's trying to do a little bit of both chronology, but also kind of typography. What is AI? I use this phrase. It's an intellectual wild card right now. People use it when they don't know what they're talking about. And yes, I have Mark Zuckerberg in mind. But there are many, many things that are not classical human imitative AI of the Turing or McCarthy style. There's some, augment humans' intelligence with computers. A search engine does that. It takes in massive amounts of data, it processes it, it makes us more intelligent. That's what's been happening for the last 40 years. And there's something else like Internet of Things and data flows and the medical system, commerce and all that. So the big systems level, if you put a thing around that, that's another kind of thing. I would not call all those AI. I think that's just not, first of all, none of it's about intelligence per se. And thought, that's not about thought. It's about systems that work and make predictions and make inferences and decisions and so on and so forth. So it's not about thought, so calling it or intelligence per se. It's about systems.
So I would like to address both of these topics with my own perspective. I completely agree with Michael in terms of right now, data science, whatever you want to call it, what's going on in what people call data science is an umbrella activity. It's one of the reasons that I think that the way in which Columbia structured the Data Science Institute makes a lot of sense, at least for now. And whether it will evolve into a college or a school, that's for the future to determine. But right now, in terms of the way that data science is an umbrella activity, it involves multiple disciplines, for sure, foundational ones like math and statistics and computer science and EE and so on, but also every other domain on campus. And so the Data Science Institute at Columbia, for instance, collaborates and brings in faculty from every single school, law, business, journalism, medicine, social work, you name it. Many faculty are part of the data science effort on campus, and I think the same is true at Berkeley. And the same will probably be eventually true at most other campuses. So umbrella activity, whatever you want to name it, it's happening because everyone has data and everyone wants to do something with that data in terms of extracting the knowledge and information and the value that that data contains. So that's the umbrella thing, and from that word, umbrella, I will agree with you, Mike. On the second question of AI, this is just me liking to partition the world, but I see AI, data science, machine learning all overlapping. I see they're not all the same thing. I think the AI community would say machine learning is part of AI, and the data science and AI and machine learning overlap. Data science involves more than just the analysis of data. It involves everything from generating data, collecting data, processing the data, storing the data, managing the data, visualizing the data, interpreting the results, and so on. There's the analysis is what has made data science so cool now because of machine learning, and machine learning is part of AI. So that's my partitioning of the world. And of course, the database people are going to think that they are part of this entire spectrum of the data life cycle. We can't do without them. And by the way, when I think about in computer science, the big data and so on, this predates deep learning. If you go back to Jim Gray's
No, deep learning's from the 1980s.
Okay.
All the ideas were there. David Rumelhart, I don't know if his name has been mentioned today, but it was all there in the 1980s.
Jeff Hinton and I were colleagues at Carnegie Mellon together when he was first.
My advisor was David Rumelhart, and he did back probably in 1983.
So, but the point really is that I think if one thinks about the data life cycle, then one can see that there is plenty of room for people who are doing data collection, data generation, even people who are inventing sensors and so on, all the way to the analysis people, all the way to the people who are doing the visualization and so on. And of course, the data management, data storage, database, information retrieval people see themselves as part of that data life cycle.
I find it just totally remarkable that on my bookshelf in my office, I have a 4-volume handbook of artificial intelligence, which some of the people in the audience probably have too. I think it dates from like the 1990s, early 1990s. It's a few thousand pages of material. There is nothing in there about probability, about probabilistic inference, or about data, or statistical inference, or data science, or anything like. So it's a handle that has completely changed in what it appears to me.
It's a branding. And so I will push back on. I do not think machine learning is part of AI. That's just not historically correct. Most of the current thing, machine learning, is kind of optimization, control theory, signal processing, statistics, et cetera, and that stuff was pushed out of AI for most of its history, and it developed completely separately. It has its own conferences, its own history, its own culture. And so putting the word AI on all of that is just historically just wrong. My statistician colleagues they'll call themselves machine learning if they have to get the grant money, but they're not going to call themselves AI. That's just that's just not right.
But lots of other people will.
Lots of other people will
Yeah.
in industry and the newspapers, and people will grudgingly go along. But their aspirations are different. Their aspirations are not that of McCarthy of trying to put thought in a computer, which is a great aspiration. Absolutely nothing wrong with it. Their aspirations are very, very different. It's to try to figure out what's out in the world, help do science, help build engineering systems, help make decisions, and so on and so forth. And decisions not of the kind that humans make, but decisions that have to be made in the real world because the real world is the way it is.
We have about 10 minutes. Would you like to take some questions?
Sure.
Yeah.
If you'd like to go to the mics, if you have any questions.
Uh-oh, someone even more provocative than me.
Andrew.
Yeah, I'm in trouble.
Either you or me.
Yeah, I'm not thrilled with your crowd-pleasing academia bashing. Let me just say that the
Come
problem...
close to the microphone. We don't hear very well.
I had one bone to pick with your crowd-pleasing academia bashing in that I think that the problem of communication is difficult outside of academia also. I think there are a lot of people who do statistics or the equivalent within companies who have difficulty communicating too. So I think the issue that David mentioned about having statisticians spread out all over the place is a real issue anywhere. But the thing I wanted to ask, it came up actually in the two previous keynote talks, which were so amazing. And what it seemed, I wonder whether a lot of applications have a kind of a last mile problem in that there's this incredible inferential framework which allows computer scientists to solve problems that we couldn't solve before, and I guess it allows statisticians to do it too, because we can run the computer programs that computer scientists write for us to do deep learning, and it's just amazing. But then I wondered, like at the end of all this, like there might be a development of a new drug, and then it gets tested using this very crude approach where all of the depth gets forgotten, and you just have two groups of 200 patients each, and they check the p-value or whatever, not using all the structure that came before. And so I wondered what you all think about that, like the integration between, like if the problem is recommendations on the computer, it's kind of fine because there is no last mile, it like goes directly into your computer. But if the problem is something like drug development, then is there a way to kind of connect that to probabilistic understanding?
So I don't think you're pushing back. I agree completely with everything you said. Maybe another slightly different way to say it is that the focus of the machine learning crowd right now is all on pattern recognition. It's dude and hard on steroids. If you're a statistically minded person, there's two sides to the field: pattern recognition and decision making. And decision making is vast. Even making one real world decision, that's consequences. It's not about just gathering data and getting out an output of a neural net. So think about going into your doctor's office. The doctor measures your genome, your height, your weight, your blood pressure, and so on. 40,000 dimensional vector goes into a neural net. If the number that comes out is over 0.7, you're supposed to have a heart operation. It comes out to be 0.701, right? Is that the end of it? Is that the decision? Yeah. No, you're going to have now a dialogue. You're going to say, what's your error bar, first of all, but you're also going to say, what's the provenance of the data? Where did that data come from? Is it about people like me? How old is it? What machines were used? You're going to say, do what if experiments. What if I were to do more exercise? What if this or that? Which is going out beyond the data at hand and thinking about other kinds of data. And that's just one decision at one time. Real world decisions are about collections of decisions all being made jointly about economic consequences of all those things interacting. And so you can see the vast scope of it. Currently, machine learning is all focused on neural nets and deep learning and pattern recognition, taking in labeled data, and that's all it's about right now, mostly. Now, if you go to the research conferences, no. But that heritage of decisions plus inferences plus data, that is the 300-year-old statistical heritage. And that's what we should be inheriting and pushing forward and making computer science real, that really works in the real world. So I agree with everything you said.
Question? We can't hear you. Oh, there we go.
Thank you for the discussion. I'm a student from UCSB. You mentioned the recommendations are not just about movie recommendations. Soon we will be recommending medical treatments and we'll have more important recommendations. So what are your ideas of democratizing those models that we will deploy in the world? Do we get one training sample per person on the planet, or do we get one training sample per dollar paid or per CPU owned, or how do you think we should go?
Easy saying. I got a simple answer that you're not going to like, but it's markets instead of just computer science a company telling us what to do. So imagine I go to Shanghai, I walk out on the street and I want to eat. I'm hungry, right? And I don't speak Mandarin, and I don't want to get a list of advertisements. I don't want to get a list of recommendations from some company that thinks they know about me or they've followed my browsing history, right? Rather, I want to be connected to all the restaurants around me by a mechanism. And it has to have a little bit of a recommendation. It knows about that I like Sichuan cuisine. It knows I have a certain price point. It knows some things about me, but not everything. It doesn't know my mood in that moment. And then I want all the restaurants to see me on the other side of a market. And the restaurants look at me and other people like me, and they start making offers. We have a matching protocol. And so we have recommendation system on two sides, matching protocol, all a big happy market. Now, not all of us are going to get sent to the same restaurant because it's the most popular restaurant or somebody rigged it or something. We're going to participate, and it'll be more democratic just because we all have a preference that the companies don't know. So I think the IT companies don't get this. I think they're just seduced by the advertising model. The advertise model is that we know everything about you, so we can tell the advertisers, and so they can advertise to you, right? If you get off that mentality, you say, no, I want to connect you to the restaurants because you guys are going to know about each other in a way, and I'm just going to help out and sit back. So yeah, democratization is a great word, but to me it's mostly just about starting to think about markets instead of services that we provide to people because we know everything about them.
Thank you.
There's a very, I think a lot of companies have been talking about what people are calling data marketplaces and data exchanges.
Yeah.
And this is really getting at a question of what is the value of data. And of course, that's a big question, and there are lots of nuances to that question. But the idea of a data marketplace, I think, especially where you're talking about doing some matching on both sides, seems very promising.
Yeah, no, the
But
word market is
it
one.
changes the paradigm, as you're
It should
saying.
be embraced. It's not been embraced.
Yeah.
But markets are mostly, 3,000 years of markets have made us rich, happy, and wealthy. We would all be up in the trees still if we hadn't started to come together and be trading and having markets. And we can create new ones that are, in domains like, finance or music or whatever. We connect producers and consumers in new ways with all of our data instead of just trying to think of it as we get data, we don't give you any value, we advertise based on it. Or maybe we'll give you a little bit of data market, we'll give you tiny amounts of money because your data is that. I mean, I agree with the principle there, but it's not, I think there's much more to exploit about people who have not been ever connected before can be connected, and now a market can be created on that.
Who was next? I wasn't paying attention.
So
This side.
I have a comment to make and quick questions. The comment is among the different models you mentioned earlier in terms of a data science program. I would like to mention at Penn State, we have an undergrad data science program that started 4 years ago, which include 3 colleges currently: computer science in engineering, statistics in College of Science, and College of Information Science and Technology. And so the programs drew courses and faculty across the colleges. Now we are expanding other colleges to include application domain areas. So just a brief comment. The question I want to ask to the panel, instead of thinking about what data science mean currently, whether it is from the real world, the industry drive, or from academic discipline viewpoint, I think my question is, what do you see the relationship between data science and causality?
And causality. I'd say.
I mean, causality's been around for 100 years in statistics, so it's in.
Yeah.
And maybe to be a little less facetious, causality is about knowing if I turn this knob, something will happen in the real world, right? And if I'm going to affect the real world, as we've been arguing we should be, do public policy, do systems that work in the real world, I got to know what things to twist to make the real world react, and that's causal inference. So it's been around for a long, long time and still always will be.
I want to say another comment about the data science in academia or industry. It doesn't really matter. One of the reasons I think we need to take this question of what is a data science seriously and have some control over what it means is that I think in industry, the title data scientist can mean a lot of different things. It can mean anyone from who's doing data cleaning and data wrangling all the way to someone with a PhD in machine learning. And industry itself is grappling with that problem because when you're advertising for a data scientist, what are the skills that what you really want for that? And this is where industry and academia can actually have a conversation, because we in academia are producing people with data science skills through courses, through degree programs, and so on. And we should be matching the needs of industry and talking with industry and saying, well, this is what it means to be a data scientist.
One last question.
Great. I think I'm next. So I love that you framed much of what we call data science today as engineering and, in fact, really problem solving. At the same time, there's a difference between problem solving and engineering. Engineering has a robust basis in understanding science. We license engineers and we expect them to have some fundamentals. And I see way too many data-driven problem solvers who ignore that, who go out, who take data and have no idea of the distributions, who take survey data and don't know about the sampling and go and do things. So do you have thoughts on what we will require of the future engineer data scientist to believe that, to master in the way of basic training, to be able to carry out this profession responsibly?
Well, in some ways it's obvious. It's got to be everything you just said. You know, statistical inference ideas meets computational modularity and scalability and modeling ideas. So let me just allude to something we did at Berkeley. Our freshman level class has become kind of famous now. And we designed this to be a Python class, effectively. We're going to teach you Python programming, all right? But wherever you had a kind of classical, what are you going to use this for? And the answer was maybe a Fibonacci series. Or our example will be, we'll teach you how to play do a game. All right, take that out and put in a statistical inference problem. All right, so if you go into industry on day one, you're going to probably be asked to do an A/B test. All right, here's our website before, we're going to tweak the website, here's the website after, is it better? You're going to have 1,000 people on this website, 1,000 people here, you have 2 columns of 1,000 numbers. All right, so I did a little experiment. I went to my computer science colleagues at Berkeley and stood up and said, we're going to teach a class where we take out Fibonacci series and we're going to put in an A/B test as exercise number 1 in the class. We're going to teach just enough Python to do such thing. Can you guys give me an idea of how you would solve that A/B test? 1,000 numbers here, 1,000 numbers here, are they really different? And I couldn't get any of my faculty members to say they knew how to do it. Someone sort of raised their hand and said, well, maybe a t-test? I said, wait a minute, there's no Gaussianity here. These are 2 columns of numbers. No one knew about a permutation test, which is a beautiful, simple solution to this. It gives you inferential, beautifully done. And all you need computer science-wise is to permute lists of numbers again and again and again. So students can learn to do that, and they can love doing it with Python, and then they can try it on real data, and they can actually make real inferences, and that's like after 3 weeks in your freshman year. And then you repeat that cycle about 10 times during the semester on other topics, and someone comes up at the end of that, knowing how to program in Python, but knowing how to solve real-world modern data problems, and then actually having done work with real data, and coming out super excited. So we have 1,500 students in now a semester taking the class, and they love it.
Jeanette gets the last word.
I want to speak more sort of just because Mike talked about the Berkeley Data 8 course, I just wanted to convey the rigor of the master's program that we have at Columbia, where we require 3 computer science courses and 3 statistics courses. We also have a capstone course, which is where we usually have an industry affiliate bring in real-world data. Our students are working in teams, solving real-world problems, and that is also when we raise questions of data ethics. So we try to do in the 7 requirements plus 3 electives to at least set a bar for what it means for someone coming out with a data science degree. And this is a very rigorous program, highly quantitative.
Super. Would you like to make closing remarks? We're out of time. That lies. It's actually 3 o'clock.
Oh, well, no.
Go ahead. Say something grand.
I get to say something grand when we close, so you can say something.
Okay. Now is the time. Do you want to take the podium, or do you want to do it from where you are?
I'll take the podium.
Okay.
This is Jeanette wearing multiple hats. Actually, I'm really substituting for someone who couldn't come at the very last minute. So first of all, I want to thank all of you. We have to close immediately, but I understand that not all of you heard my introductory remarks. I'm not going to repeat all of them, but there are a couple that I do want to emphasize. That is, first of all, ACM and IMS have agreed that we want to continue this event. It will be focused on foundations of data science. And we want to bring in other organizations to represent the other fields that contribute to the foundations of data science. And so, so be on the lookout for this event to happen again with other fields and other organizations participating. So thank you very much for staying the whole day, and I hope you enjoyed it. Thank you.